everybody. Holy cow, let's try this again. I'm going to need your help right now. Good morning, everybody. Yes. You got to be excited because you're here for the first ever Sysdig Camp-Con-World-Fest-Summit. Now, when you saw the name, did you think, is this thing for real? Is this a joke? We weren't sure in the beginning either, actually. So I need to see a show of hands here. How many of you have been to some kind of camp, like coding camp, boot camp, something? Show of hands. Base camp, something, right? Everybody almost. Okay. Con, Elasticon, RubyCon, something? Yeah, okay. About a third of the audience. World? Yeah. Oracle World, if you've had to do it, I'm sorry. There are therapists in the other room if you still need them. Fest, have you been to a fest? Usually beer involved. There will be beer here later. All right, and a summit. Right, but how many of you been to all of them at the same time? That's what I thought. That's why you're here today. It's going to be awesome. My name is Apoorva Dave, part of the Sysdig team. I'm also doing housekeeping. Okay, so first of all, check. We talked about the name. That was number one on my list. Number two, wanted to make sure you know you've got an agenda on the backside of your badge. We already have one slight adjustment to the agenda, which is we're moving the break up to 10 o'clock. So the break will be from 10 to 10:15, and then everything will proceed almost normally from there. Other critical announcements, restrooms are back over there, coffee over there. You can just keep making the laps. Wi-Fi, you should see it already. We've got it posted on the pillars over here. The Wi-Fi name is Sysdig, and the password is CCWFS-2016. A couple more announcements. Downloads. So as you probably read when you signed up, this is going to be hands-on. We're doing as much as we can lab style, and you should have gotten one of these little sheets of paper. When you signed up, they have the information for the downloads you need to make those labs worthwhile. So make sure you grab them as soon as you can, and you'll enjoy the conference that much more. Finally, if you're a Twitter file, I don't know if that's the right word. If you like to tweet, we're using a hashtag Sysdig 2016. We'd love you to join in. It'll be a lot of fun. And one last announcement, prizes. No conference is complete without prizes. Do you like prizes? Does anybody like prizes? Kind of mediocre. You're not really into free stuff. That's what I get so far. We've got a couple prizes. So first of all, you probably saw the drone by the registration desk. So we're using that for the 4:30 Find the Hacker contest involving Sysdig Falco, which I think you'll think is pretty cool. And also, as some bonus prizes, we have a bunch of Starbucks gift cards. And I like to run a contest I call Stump the Presenter. So whenever, if you can stump any of the Sysdig presenters during the labs, you'll get a Starbucks gift card. I'm sparing our guest speakers from being stumped, so guys, you're cool, don't worry about it. But for Loris, Luca, John Luca, and Mark, if you can stump them, there's more caffeine in your future. So with that, I'm going to get out of the way and introduce the creator of Sysdig, the founder and CEO of the company, Loris Degiani.
Thank you, Purva. Can you hear me? Is the mic? Okay, great. Welcome to Sysdig Camp-Con-World-Fest-Summit. I think I cannot even say it. I think that was my goal for the day, saying the name of the conference right. I will have to practice more. I'm very happy and very proud to have you guys to our little conference. When I started working on Sysdig a couple of years ago in the spring of 2014, I was definitely not expected anybody to really pay attention to it. So being here now with you guys, spending a day with us, makes me really happy and proud. I have 10 or 15 minutes just to give a welcome for the conference. I wanted to do it in a way that is maybe as bit different and can bring a bit of value to people. So I decided to do a short history of Sysdig in 7 command lines, so that every command line can be something useful that you guys can bring with you. Before doing that, a little bit of bragging. We just passed the million downloads of Sysdig from our repository. Sysdig can be gotten from, yeah. So thank you guys for being part of this, but yeah, the user base is growing, and yeah, it's pretty remarkable to reach such a milestone. So, command line number 1, back in 2014, when I started working on Sysdig, the basic idea was I come from years and years of working with networking tools, in particular TCP dump and lib pickup originally, and then Wireshark. So one thing that I always wondered is, can you apply the same principles, in particular the ability to take trace files, the ability to have a well-known filtering language to go through the data. So this kind of basic workflow that I was used to and I contributed creating for the network, can it be applied to host, system, and application troubleshooting? So the first command line is, basic Sysdig, where you can launch the tool and filter by, for example, FD type, and you can get essentially the network activity, but in the context of the process. So not only you see what's sent and received on the network, but you can also see which process is doing that. This is something that has always been painful in the network world, so it's something that essentially I built to solve a pain that I personally had. In August 2014, we released a Chisel called LSOF. Chisels, you'll see many of them during the day, but are Lua scripts that you run on top of the Sysdig stream. And LSOF is like a less known application of Sysdig that allows you essentially to get an output very similar to LSOF, so the file descriptors that are open, but essentially do it at any arbitrary point in time. So for example, this command line shows you the output of LSOF for a specific process called my app, and essentially when this process exits, which I find very useful because it's a nice way to find file descriptor leaks or something that your process has left hanging when it comes out. So the ability to synchronize the listing, the file descriptors with a specific point in time can be, a useful application of Sysdig. In January 2015, we released what people call it with different names, but we called it a spectrogram. So it's like a console-based visualization where you can display latencies or times on the horizontal axis and the time that is occurring on the vertical axis. And this gives you these charts that give you an at-a-glance view of latencies, different types of latencies, and look pretty cool, especially when you run them just in an SSH shell, because this is just based on NC characters. We support them in Sysdig, and we support them also in Sysdig. So there's a Chisel for that, which is called spectrogram. So if you just run this command line, you will see it appear on your shell. In February 2015, we also announced support for containers. So Sysdig was essentially the first tool around both command line or non-command line that was actually allowing meaningful introspection in containers. In particular, this is a Chisel, for example, that shows the top processes with the container context with the PC flag. So essentially, you will see the processes on the machine, but you will also be able to see which containers those processes belong. And this is essentially done by doing the matching of processes and process IDs with namespaces and C groups. In June 2015, we launched Sysdig, which is our Sysdig-based top or HTOP. So it's a way to consume the data that Sysdig extracts in a way that is a bit more, let's say, user-friendly and interactive. This is how I consume the Sysdig data 90% of the time, because you have nice customizable tables that cover different aspects of what you want to see in your system. In July 2015, we announced something that is not command line. It's Sysdig Cloud. It's our distributed tool. So Sysdig Cloud leverages the same data set as Sysdig, in particular system calls and the other system events that Sysdig uses, but it tries to create essentially an end-to-end performance visualization of your network and collect metrics and offer a powerful analytics engine. In November 2015, we also announced Kubernetes support in all of our tools. So this command line here, essentially, as you can see, allows you to connect to a Kubernetes master. And at that point, both Sysdig and Sysdig, and also Sysdig Cloud, of course, are able to put these, the information coming from the Kubernetes topology in the context of the system calls or the visualizations that Sysdig is able to offer. And for example, show the top pods on the machine, or show the services or the namespaces, and allows you to drill down into the details and go essentially from the namespace to the container. This is a feature that has been extremely popular since launch, essentially. Similarly, in April 2016, we announced Mesos integration. Very similar. There's the -m flag in the command line, and then you can provide the addresses of the Mesos master. And at that point, you have similar metadata coming out and being able to, and you're able to correlate it with the Sysdig stream. There's a lot of stuff, of course. These are just 7 examples. But in particular, during the spring and summer, we kept working hard. And 2 things that we announced recently are Sysdig Falco, which is a security and anomaly detection engine built on top of the Sysdig data. We will have a couple of sessions on Sysdig Falco. It's pretty interesting the way you can apply system calls to do security-based anomaly detections, especially when you can do that in the context of containers or in the context of your orchestration. And the other thing that we're going to touch in a session today, I'm actually going to do the session, is tracers. And that's another very interesting and fun application of our system, where you can essentially do some kind of tracing and interject application or user markers inside the stream of events, and then do fun stuff in terms of measuring and filtering and extracting data based on that. What to expect today? So first of all, let me thank our speakers, both the guest speakers, like Brendan, Adam, and Matthew Garrett. So please, a round of applause for them. These are all world-class guys, and we will all learn a lot from them. And also, of course, our Sysdig team members that are going to give the hands-on sessions. So Gianluca Borello, Luca Marturana, and Mark Stem. As Apura was mentioning, some of the sessions are hands-on, and there are files to download. So this here is the link where you go to download your files. And of course, the Sysdig team, there are few people from the Sysdig team here, including myself. We're here to help you, but especially to know you and to learn from you. So don't be shy and come talk to us. In a general way, we're here to get our hands dirty. So this is, command line, system level, container, troubleshooting. So, you can expect today to leverage your low-level skills and hopefully make them better. So our goal today is helping you to go from like this to this. So welcome, and let's get this started. Thank you.
And now, please welcome to the stage the man who's going to tell us which came first, fire or syscalls, Adam Leventhal.
Hey folks, let me deal with the great problem of computing, making sure my laptop works with the screen. Great, can you see it? All right, great. Thanks, good morning, everyone. I have the kind of ignominious position here of having the least delightful accent you're gonna hear maybe all day, but definitely during the morning. We've got all these lovely Italian accents. You got Brendan speaking Australian to us, so you'll have to just suffer through my domestic accent. When I was delighted to be invited to give this talk today, and one of the things I love about Sysdig, and you already heard this in Lauras's talk this morning, is this awareness and respect for the systems that came before it. And so I want to go back and look at some of the history around system calls and system call tracing to give us a little bit of a context for the day. If you are a reader of academic papers, maybe you can think of this as the related work section of the day. So look at system calls and how they're traced, and also their rise to centrality. So I want to give first a little bit of background on myself. So I'm Adam Leventhal. I'm just one of the co-inventors of DTrace. Has anyone here run DTrace? Okay, like a few people. Good. Thank you very much for the generous folks who kind of tentatively ran their hands. Like, I've seen someone run DTrace. I also was the co-founder of the ZFS storage appliance team at Sun that was later acquired by Oracle. More recently, I was the chief technology officer at Delphix. Delphix was some enterprise software, so I'm not going to ask if you folks have heard of it. You probably haven't. Most of our customers were like chief information type and chief information officer types. I think that there are probably not very many of those folks in the audience today. But it was technology building on work we had done in Solaris and ZFS to do fast cloning around large database systems. More recently, I was an entrepreneur in residence at Sutter Hill Ventures, and here I just want to do a little public service announcement on what that means. People hear that and they think, oh, you're a venture capitalist. And they also think that I'm going to pay for lunch and buy their beer. But it's not, I'm not a real venture capitalist. I think entrepreneur in residence is not like a job. Like, you guys have jobs, you probably need to show up to a place and like do a thing by a particular time, or like someone will get cranky. It's not like that at all. It's much closer to like Silicon Valley welfare. So this is by way to say, if we go out for beers later, please don't be offended when I just chip in for my share and I'm not paying for the full round. I'm also a recent founder in a company, but that happened yesterday, so I'm gonna set that aside for the moment. I started in the Solaris kernel group, and I really think of myself as a kernel guy. My first exposure to Sysdig was 2 years ago, December 2014. Lars had reached out when he built the thing, which I thought was great to have that conversation, invited me to their first meetup. And Lars, I don't know if you remember this, but at the first meetup, there was a guy in the back of the room who was asking Lars questions. And by way of preamble, he said something like, since kernels are slow and no one uses them anymore. And I think I got whiplash, kind of my head spinning around so quickly. And Lars kind of like stepped forward like he was concerned that I was going to go after the guy. So I'm saying that more by way of so maybe there's some kernel folks in the audience, and you should be kind to us and not necessarily think of us exclusively as dinosaurs from some forgotten era. All right, so on to system calls. What is a system call? I assume many if not all of you are familiar, but it's the fundamental way that userland applications interact with the kernel. And in fact, if you're kernel folks, you kind of think of all userland applications, whether they're C or Java or Ruby or Python or whatever, they're kind of just generators of system calls, and then they do whatever it is that they're trying to do. But that's how kind of everything looks at the level of the kernel. Typically implemented as a trap from user mode into kernel mode. And they're mostly standard-ish. So if you kind of wander between Linux and Mac and other things that kind of look in that shape, you'll see open and you'll see read, and they mostly work the same. As you start getting into the fringes, you'll see some things that look weird, and we'll play with that in just a little bit. But they're very, very fundamental to multi-user systems, and we certainly take them for granted now. But they've been around since the dawn of time, since the dawn of Unix, since the early days of multi-user, multi-processor computing. So I want to walk through that a little bit. So in preparing for this talk, I started looking at what are some of the early system call tracing systems. And the only thing I could find online was this paper from 1994 about tracing Windows. But it cited an earlier paper, a paper that completely apparently unknown to the internet. But I found someone with it, and so I worked my way through getting it. I won't walk through the whole of it. When you're buying me a beer later, I'll give you the story. But I want to walk through this paper. And my apologies, it's a little small, but I'll be reading this out for the folks in the back of the room. So the paper from 1986, from Unix 1986, is called A System Call Tracer for Unix. And I just want to walk through a bit of this history because there's some great stuff here. It was done by the Ultrix engineering group, Rodriguez in it. Anyone even heard of Ultrix before? A couple of hands. OK, great. I know who my old schoolers are. So Ultrix was from DEC, Digital Equipment Corporation. Has anyone ever even heard of DEC? OK, a couple of folks. Great, even more. DEC was acquired by Compaq. Compaq famously merged with HP. The CEO of Sun at the time described it as the sound of two garbage trucks colliding, which is still just the most spectacular. Of course, went back in his face when Oracle acquired Sun. There was some squelching sound there as well. OK. So another thing I want to point out on the slide, just because it is so beautiful, DECVAX !RR. Does anyone know what that is? OK, great. So this is UUCP. This is in the days before, in the land before time. This is sort of what email looked like. Unix to Unix copy. And you'll see these exclamation point delimited routing strings, this way that I get a message from one place to the other. And forgive the diversion, but I think it's so great kind of seeing this. And the other great thing about this conference from 1986, Unix 86, was not just this paper, which I'm going to go into a little bit, but also all the other stuff. The same author presented a variant of VFS. There was another variant of virtual file system from a Sun presenter. There was a description of Mach, one of the early descriptions of Mach, the kernel from CMU, architecture from CMU. And then at the same conference, there was also this seminal work in mail routing using domain names. So very germane. I'm glad that this conference happened. Turned out to be pretty important. All right. So at this conference, there was in this paper, there was this observation that system calls and time spent in system calls really matters. And you'll have to indulge me, I'm going to read you this quote. They're talking about profiling techniques. Most of the profiling information is oriented towards the local user functions and not to the calls into the system. This is not a criticism, since local user functions is what the user can change, are what the user can change. However, it does point out an area where a lack of knowledge exists. It is often assumed that system calls are negligible, or something not to be worried about. An overabundant use of system calls in many instances can result in havoc just because the programmer didn't know the difference between a system call and a library call. Single user systems don't have to count system calls, but multi-user systems do. They have to hoard system calls and treat them with respect, since only one system call can be accomplished at a time per CPU. OK, I love everything about this. Also, if you're getting a little queasy reading this, and it looks like maybe I took a picture of it with my cell phone and screwed with it with Photoshop, like, there's a reason it looks like that. That's exactly what I did. So my apologies. OK, but a couple of important points here. This identification of system calls as an important point to look at the system, something that hadn't been looked at before, where spending time in system calls was especially germane. And if you can believe it, that only one system call at a time per CPU could be executed. Obviously not true today, but even more glaring as a point to go look at. OK, one other piece of text, and I promise I won't do this to you again. Consider what information could be obtained if the exact time-ordered sequence of calls was given. A complete trace of the algorithm being used to be found in this data. The traditional profile information gives a conglomeration of the usage, often masking algorithmic data. The complete trace of the program, however, produces more data than one can imagine. To pare this down, consider only a trace of the system calls that a program uses. Although the complete picture is not available, it's often a strong indicator of what's happened. OK, a couple of things here. The big point here is his observation that system calls are these waypoints. It gives you the right kind of granularity where you can understand more or less what the program is trying to accomplish without getting bogged down in some of the spots in between. It is, of course, a very kernel guy way of looking at the world, right? That system calls are the things that matter, and then everything else is just noise in between. But the other great thing is this observation that tracing everything, a full trace, is more data than could be imagined. right? It's inconceivable that if you were to log every message all the way through. A little bit quaint, but still kind of true. Still true that it would overwhelm you. Okay, so briefly how this system worked is that if you're the process and you're invoking a system call handler, the tracing program can open a new device called DTrace. It creates a buffer into which data goes, and a lot of this might sound familiar. And then if tracing is active, it then logs that system call into the buffer. It executes the system call and then logs the return values into the buffer. And then later on, the tracing program can go grab the data out of the buffer and present it back to the user. Okay, so there's a small disabled cost. Every system call is now executing a conditional to decide whether tracing is active. But it was the 80s and probably no one cared. Interesting system where you're logging this in-kernel buffer, and of course, very important that you read out the buffer at a reasonable frequency, and so that the buffer doesn't get lost. But the system also accounts for drops in your traces and the knowledge that this can be lossy. Okay, this is 1986, and you'll see this mirrored in some of the systems that we're going to talk about later, and even mirrored in Sysdig today. Just, again, another quick aside. I think this paper is so phenomenal, and forgive me for like the little papers we love vignette inserted into the middle of the Camp-Con-World-Fest Expo. But first, this is a Unix paper. This is ostensibly an academic paper. There's a section called System Call Traces and Fixes, and it says, now for some goodies. And the goodies are traces of unoptimized programs like PS and LESS and HEAD, knowing that the people reading this, they want to see the action. They want to see what actually happened when you trace the thing. The other great thing is there's a line in this paper that says, by accident, I actually traced a CC command. It's kind of like, this is like its blog of its era. This is kind of, if Twitter existed, he would be tweet storming this thing. But instead, in 1986, it was an academic paper. I love the idea of this Wild West, this frontier of systems research and technology. But part of this, and one of the things they observe in this paper, is that this technique is hard to make secure. You're kind of giving people access to look at everything, and in particular, he kind of head-scratchingly in this kind of musing format that I'm alluding to, notices that, well, if you give people access to everything, then they can kind of sniff other people's passwords, and that might be a negative thing. Maybe we don't want that. So this system existed in Ultrix. I'm not sure about the user permissions associated with it. There were variants of it in SunOS, but I think not in Solaris, so gone in the late 80s. But that gave rise to Truss and to strace, which I assume everyone here has run strace, yes? Okay, a couple nods, not even gonna raise your hand for that one. But has anyone run Truss on maybe Solaris or some of these other Unix systems? Okay, a couple folks, great. So Truss was developed a couple years later in 1988. And the way that was named, I love it, is if your program doesn't work, put it in a Truss. This is from Roger Faulkner, the author of Truss. It was built on top of this new structured /proc in SunOS and Unix. And I just want to say that Roger's paper from 1991, from Unix 1991, is a seminal paper in /proc, and I highly recommend it. And I'd also say I had the great honor and pleasure of working with Roger early in my career at Sun Microsystems, and very sadly, he passed away recently. And he was just a legend of the industry. His work lives on, and I'm very honored to have had the opportunity to work with him. strace came along a couple years later. It was billed as an alternative tracer for SunOS, and then later other Unix systems, and then famously Linux a year later. And then all of the non-Linux code has been excised in 2012. So now it's a Linux-only type of thing. So contrasting these system call tracers to that first one we heard in Trace in Ultrix in 1996, I want to just walk through how these things work. Because I think we've all trust things or strace things and not kind of appreciated necessarily the machinations that the system is going through. So first, when the process invokes a system call, it triggers a breakpoint. The scheduler stops the process. It wakes up the tracer. The tracer then records the arguments from it. It tells the scheduler to go wake it up. The scheduler stops the tracer, wakes up the process. Process actually executes the system call, does the work of the open or the read or whatever. Then we stop the process again, wake up the tracer, record the return value, signal the process, stop the tracer, wake the process, and finally we proceed. And we do this for every single system call. Now I'm going to kind of stage dive into your hands. Any problems with that people see? Yeah? Right, so to summarize that, massively slow, right? You're causing all these context switches all over the place. And actually stealing from my former colleague, Brendan Gregg, he had his own kind of cheat sheet for strace, which I just love. strace the command, that's how you slow down the target and print the details of every system call. strace minus ppid, you slow down the process and then print the details for each system call. And he kind of goes on like this. So you can hold this up. You've got in your hands that they gave you this morning some strace cheat sheets, the comparison between Sysdig and strace. I think some of the and slow down the process is left unsaid in that, but you can read that in from now on. So massively slow. And as a result, it's also basically unsafe to use in production. Has anyone like straced maybe a database in production or a system in production? Is anyone brave enough to raise their hand and like admit they've done that? Okay, one brave soul in the back. Great. Okay, so obviously those people are not to be trusted. It's maybe in some limited circumstances, but it's not a production tool, and it's not designed for production from a performance perspective. Certainly, there's also safety elements where if one of these tracers dies in the middle of it, all of a sudden you can have some stray breakpoint that your process is just going to be killed on. Because I've been given the microphone and I get an opportunity to vent and I'm getting to be a cranky old man, I started using Go for a little bit, ran the debugger on it for the first time, and it promptly died and killed off my process, which had been running for 6 hours. So this is like the cardinal sin of diagnostic tools and frameworks. You can do no harm, right? If it is responsible for killing your program or changing its state, it's really bad news. It can also chase the program away, the problem that you're looking at away with strace or truss. And I don't know if folks have seen this. You're seeing some kind of nasty race condition. You run strace, and all of a sudden the problem's fixed, which drives you kind of insane. Because strace or truss are serializing these programs. In Solaris 11, there was some work to make truss multi-threaded. So every thread in your program would have a thread in the tracer. So it removes some of these effects, but it's still kind of a mess. And again, useful for debugging in development, but not really in production. All right. So now I'm going to transition from the papers we love talk into maybe a show Hacker News section, but I promise I'll be brief. So DTrace is one of the systems that I worked on. It's the dynamic tracing framework. We first shipped it in 2003 and 2004 in Solaris. It's now in Mac OS X, FreeBSD, a couple of Linux distros kind of off to the side, but notably Oracle Linux. It's safe by design for use in production. And this is one of the ways it distinguishes itself from some of these other systems, from strace in particular. And its goal is to provide these concise answers to arbitrary questions. In that first system that we looked at and in strace, you're mostly getting this fire hose of data. DTrace's goal was to limit the amount of data that you're getting out of the system to only get the essence of what you're asking. So not to optimize the channel from data collection to data presentation, but to optimize at the source so that you're recording only and exactly the data that you want. It's systemic in scope, meaning you can trace everything from Java to I/O, and of course to system calls. But system calls are a really common place to start. So I'm going to go get out of my slides and go type into a terminal a bit. So for those of you on Macs, when I see a lot of like illuminated Apple logos, and I'm choosing to assume that until this point, you've kind of been like me, kind of unable to not reload 538 at like a minute-by-minute basis to check on the election. But now you can use it for other purposes too. So if you have your Mac, you can sudo with me and play with DTrace a little bit. Folks in the back of the room, can you see this at all? How about a hand if you can see it? Just at the bottom. Can you see it at the top? Ish? Can you read it? Wow. OK, I'll make it even bigger. Great. OK, so we're going to just do a very little overview of DTrace. And I'm not going to try it here, but I think system calls are honestly the place that I always start my investigation of a system. And so much so that I think, but I'm not going to try, I think I could do this with my eyes closed, but I'm not going to try it right now. So DTrace is a command. You run it as root. I've done a sudo bash. And it'll give you like a nice little useless Unix-style help message. But if you do dtrace -l, it'll show you all of the probes on your system. So that's dtrace -l. So this is everything from system calls to function calls in the kernel to userland, locking primitives, and so forth. But right now, what we're going to do is look just at system calls. So I'm going to do dtrace -l -n syscall : : So in dtrace, all probes are divided into the provider, the module, the function, and the name. We have different providers, and in this case, we're using the system call provider. So I'm just going to list out the system calls on this system. And again, as I said before, a lot of these system calls start to feel pretty standard. Like if I scroll to the top, you'll see things like, oh geez, I have to scroll way up to the top at the latest version of Mac OS X. Like things like unmount and statfs, things that you probably see on all these different types of Unix systems, pread. Of course, you get to some like weirdo __ Mac get file. So OS X does things kind of its own way. Excuse me, Mac OS does things kind of its own way. All right, so that was just listing them, and now I'm going to remove -l, do dtrace -n syscall : : and print them out. And there were 1,000 entry and return probes. So this is kind of like if you could do strace for everything on your system. And it's a massive output. Someone I was talking to before the conference said it's like doing TCP dump over an SSH connection where you're just getting this feedback loop. And that's exactly what we're getting here. DTrace is making system calls, which is printing to the terminal, which is making more system calls, which is tracing more and more and more. OK, great. So I can control C that. But I can see who all is making the system calls now. As I said, DTrace is dynamic. It's dynamic in particular in that it allows you to see, to choose what kind of information you're tracing. Rather than being static, more or less static, like strace or this trace command, it lets you trace what you want. So in this case, what we'll do is we'll trace the exec name, which is the name of the executable running. So if I do that and hit return, now it's going to tell me that, like Docker, I don't know why Docker is busy, but that's kind of interesting. Maybe we'll dig into that. And I'm getting tons of drops. OK, wow. I honestly always, now I've typed this command a million times and I always learn something new. OK, so this was still kind of a mess of data. And I said something earlier about how we're trying to limit the amount of data. And here's some of the places where I think Sysdig started or was looking over its shoulder at DTrace in some of its design principles in terms of giving the user comprehensible answers. Here what I've done now is I'm using a primitive called an aggregation. It gives you a little key value from the key being here the executable name and the aggregating action to be account. For every system call now, entry and return, it's going to tell me the name of the process executing the system call and the number of times it's done it. Now, when I hit Control-C, it's going to give me that output, and that's a much more concise form. I can see, like, much more succinctly that, you know, here are the processes on the left and the number of system calls on the right. And now I can dive down a little deeper, and I assume everyone is interested in the same thing that I am on this screen. Yes, Docker? Is that what everyone wants to know? OK, I'll just assume that the answer is yes. So now I can limit my, my access using a predicate to just look at Docker. Let me explain what this is doing now. I'm honestly curious. I've never seen this before. So exec name equals Docker. This might look like awk-like syntax to the folks who raised their hand when they said they'd heard of Ultrix. So awk-like syntax where you can say this is a predicate, only do it in this circumstance. And now I'm looking at the probe function. Great. So now we get to see what Docker is doing on the system. I hit Control-C. And it's doing this event QoS thing. That's very interesting. To my knowledge, it should be doing nothing. So it's a little bit surprising that it's doing nothing. So the final thing I'm going to do is limit my access to just the k-event QoS system call, and then hope that my colleagues over at Apple have done a good job with userland stack traces, and we'll be able to see where in the Docker process it's doing this. And I hit Control-C, and now I could pop open the code for Docker and see where it is exactly that is invoking this. So what we've done is gone from a system-wide type of problem, what's hitting system calls, to a particular stack trace that identifies within Docker where this generation of system calls is happening. And this is the kind of iterative approach that drove DTrace. All right, back to PowerPoint. DTrace can do other stuff not associated with system calls, obviously, but I think system calls are the most important. And as we learned from that first talk, provide these wayposts, give you the right kind of granularity to understand what a system is doing. Now I'm going to step back for a second. I mentioned earlier that I spent kind of a long time at Sun. So I wanted to just mention Java. Does anyone remember what the tagline for Java was maybe 20 years ago? Write once, run anywhere. And it's so kind of adorable. Like, what does it even mean now? Like, I can't even imagine what that really reflects today. And just I want to mention that they also kind of used the same kind of theme. It was kind of the write once, name everywhere. So from a windowing system to a desktop to a management console and even the stock place, they renamed Java, 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 and Java. Even the stock ticker was Java. And I'm just showing the lump there, not the deep crash. Anyway, but just write once anywhere, run anywhere. I want to put it in context, because in 1996, when Java came out with this catchphrase and when it was really germane, like run anywhere actually meant something. Like it had some real significance. You had this cacophony of different server operating systems, from Chew64, AIX, IRIX, Ultrix, I think, was no longer in vogue. And then you had this litany of different microprocessor architectures. You had this real complexity in the deployment environment. And it was a real challenge to figure out how you would write a program and how it would execute in someone's lab. Now, of course, there's a bit of this today, but it's very different. So in 1996, the idea was that Java would inject this new idea, or this kind of newly new idea, this retro idea of the virtual machine, and it would be able to sit above the fray. Doesn't matter what operating system, doesn't matter which of these dead CPUs you're using. From Spark to Alpha to MIPS and so forth. Doesn't matter which of those you're using. The JVM would solve all of those problems. And of course, the phrase I learned as I was researching this is that people coined was write once, test everywhere, which is what ended up happening. But Java was only kind of half wrong here. And they were right about this idea of virtualization being a key element to solving the problem of ubiquity. They were wrong that Java and it was going to be solved at a language level. So write once, run anywhere, like today. Like basically, we just assume Intel. Intel everywhere, x86 everywhere. Like the only other microprocessor architecture that I think people typically care about, of course, is ARM. But it's pretty bifurcated in these environments. It's changing a little bit. You're starting to see folks talk about ARM in the data center and ARM public cloud, and folks with RISC-V are making a different kind of challenge there. But the landscape has gotten much simpler. In fact, if WebAssembly was really just x86, it would mostly just be fine, because you can kind of just assume whether if it's x86 and ARM, it's going to execute everywhere that matters. Of course, it matters even less because the everywhere is also Linux. And this pains me as someone who worked on different operating systems through the years. And oops, where am I going? But But obviously Linux is this ubiquitous operating system. You can assume Linux, x86 pretty much everywhere. I'm sure folks here, although they're maybe not raised their hand for it, have some Windows running in the server environment somewhere. But it's still an assumption you can make. And of course, containers make that even more true, make it even more the case that this notion of run anywhere is even more quaint. Because if you just run inside of a container, you're making assumptions that are generally true about instruction set architecture, around operating system, and then just even around packaging and package management, all this stuff, it's just solved for you. Which makes this 1996 notion of write once, run anywhere just really almost incomprehensible today. So this idea of the Linux system call layer has just gained such primacy. You've got container environments even on your Mac and Windows. There you've got an embedded version of the Linux kernel executing those system calls, executing those environments. Using virtualization. You've also got folks like the folks at Joyent who've taken a different operating system, their Open Solaris derivative called the Lumos and SmartOS, who are deploying containers, but there they've done it by emulating this Linux system call layer. We've gone from 1996, where there was this cacophony, again, of different environments, different operating systems, different instruction set architectures, to the Linux system call interface as perhaps the only interface that matters, like the level of abstraction at which now we are all operating. And this brings me to the end, where I just want to observe that looking back on system calls, we've got highly significant events, as true 30 years later from Rodriguez's paper in 1986, where system calls tell you so much about the system, tell you, and provide it at the right level of granularity, where it's not too much and not too little, but you can really understand at a high level what these applications are doing, and today what your clusters of applications are now doing. It's also a very well understood domain for tracers, well understood domain for debuggers, and something that's easy to latch on and to hold on to. And now we've moved into this era where Linux containers and the Linux system call interface has become this de facto ubiquitous standard that we can all assume in our processes. So this creates just absolutely the perfect environment for Sysdig, where you've got the right kinds of elements to be traced in this interface that has now become ubiquitous and can be assumed in all of these different instances. All right, thanks very much for your time. I hope you enjoyed it. And if there are questions, you can raise your hand. Yeah.
We've got some mics. We are live streaming the event, so if you have a question, raise your hand and we'll bring one over to you. Yeah, question in the back. Hold on. We're live streaming, so.
Hi there.
Yeah.
Are you going to update your slide deck on slideshare.net with the missing bits?
I'll not only share these slides, but the meticulously scanned and tweaked images from that paper and from a couple of others that I cited. I'll put them on SlideShare, but I'll probably tweet them, during the break or something like that at AHL. Yeah.
Right here, Sylvie.
I thought you would be talking a bit about how DTrace is different from Sysdig, or is that later?
It's not later. So how DTrace is different than Sysdig, great question. So I'd say that one of the big differences in DTrace is where and when it's intended to operate. DTrace is always available in production, but it's not always enabled. The goal with DTrace is to make sure that there is no impact when it's not being used, and then when it is being used, to have that impact scaled to the type of question that you're asking. That is to say, for the way you slow down the system to be proportional to that. And again, not always enabled. And one of the goals of DTrace is to minimize the amount of data that's being pulled from the source, from data generation, to the edge, to where people are using it and consuming it and observing it. Sysdig, in contrast, I think is most useful when it's always enabled. So there's more optimization that can be done, or there's more optimization that has been done around to make sure that those pieces are efficient. There's also, Sysdig is more of a stream of data because the post-processing or the observability happens later in the flow, where then your stream of data, and this reflects some of its origins from Wireshark, or from Loris's background in Wireshark. You've got a stream of data that you're then paring down to answer questions about the system. It's also much more germane for distributed systems, where DTrace is focused on single system analysis. So those are some of the differences. I'd also say that, again, I think one of the most salient ones is always enabled, not enabled, and then optimization. Sysdig has done great optimizations to minimize and make efficient execute that stream of data, whereas DTrace has done basically no optimization around marshalling and unmarshalling data, or like a JIT for execution of its instrumentation, because of that difference in domain. And I think the key one being always enabled versus not. Just a great question. Any other questions? Yeah.
Would you briefly describe the nature of the hooks that Sysdig uses and DTrace uses?
I'm going to talk about the hooks that DTrace uses, but I'm going to leave the hooks that Sysdig uses for someone who works at Sysdig and knows a little more about it than I do. So what DTrace does is, when you're not using DTrace, it's a fully optimized kernel. There's kind of no differences in the way that it operates. But with system calls in particular, let's say you're enabling the open system call, then very much it goes from the fully optimized system call to replacing the pointer to like the function that is invoked when a system call happens, to one that contains kind of an if tracing enabled, execute the system call, if tracing enabled for the return. So it actually looks very similar to that 1986 paper, except for the difference between Ultrix trace and DTrace with regard to system calls. Ultrix trace always has those comparisons, those branches, in the system call code, whereas DTrace hot patches that code only when system call execution, or pardon me, system call tracing is live. Great. And if anyone wants to hear me give kind of DTrace war stories, I will do that all day during the breaks or whenever. All right, great. Thank you very much.
Thanks very much, Adam. We've got now we've got a 15-minute break before we begin the hands-on lab with Luca. Enjoy. seats. It's time to get to work. All right, in the back, could we have you please take your seats? Thanks so much. Now we get into the hands-on sessions here. Kicking us off is one of the key contributors to Sysdig. Please welcome to the stage Luca Marutarana.
Thanks, Apurva. Hi, everyone. I'm Luca Marturana, software engineer at Sysdig, where I work every... The microphone is not working. No. Hi, can you hear me now? Okay, cool. Thanks. Yeah, I work every day writing system software and troubleshooting it. Let's start from containers. Tons of words that we spend about containers, so I don't talk too much. They are a good abstraction to bundle application and replicate environment and put them in production. All the containers ecosystem is bringing new challenges to us, because when you have container, you have then to orchestrate your deployment. You need to monitor them, to troubleshoot them. There are new challenges about logging, security, many of them. In this session, I'll focus on troubleshooting. Troubleshooting is a bit different with containers. All the tools that we are used to, like TCP dump, Nestat, or LSOF, top, don't play so well with containers. Because, for example, if you think about networking, every container has its own network stack. So if you run TCP dump on your host, you don't see the traffic generated by your containers. You can run TCP dump inside the container, but this means that you need TCP dump inside the container, and it's a bad practice to put troubleshooting tools inside your application containers, because they should be as simple as possible, as lightweight as possible. So all these tools have some glitches that make them not so useful with containers. Sysdig tries to solve this issue, and how Sysdig can do this. Sysdig adds an instrumentation inside the kernel as a kernel module, which is a thin layer that stays in between the system calls that all the applications do to do meaningful stuff. So the application needs to run something that is done by the kernel, and they use system call to do this. Sysdig instrument just is in between and traces all the system calls that are later available to the Sysdig command line utility on user space. So in kernel mode, traces all the events that are then available to from the user space utility to do meaningful stuff. Sysdig is able to capture system events, but they are a lot of data, as we said before in the Adam talk. And Sysdig is able to filter them, so you're able to get what you really need, but also run useful scripts on top, which Loris already mentioned. We call them Chisels. And with scripts, you can leverage this data to do anything you want. We have also support for trace files, which is a workflow that we've taken from Wireshark. And it's very useful because you can troubleshoot things offline. Like, for example, if you receive an alert from your monitoring solution and you're able to get the chart of some metric going crazy and a trace file of the system at that time. So even if you were sleeping at that time, you are able to understand what was going on. With this kind of granularity. Sysdig has native support for all the container ecosystem, so starting from Docker, but also supporting Rocket, or all the main orchestration systems like Kubernetes and Mesos. And we released it as open source, is GPL version 2. Sysdig comes in two flavors. We have a command line utility, which is just Sysdig, and a curses interface, which is we call Sysdig. They are it's the same kind of visibility, but there are different features that makes one useful for certain things and one for another. The Sysdig interface is very easy to use, so it's easy to get into all this data and get something meaningful from them, because it's a graphical interface with easy to navigate. The Sysdig command line is more powerful in terms of the thing you can do, because you have a full control of the granularity of data you want to see. You can apply all the chisels that are bundled on Sysdig, but you can also build your own chisels and run them. We will have a session later today about this. And you can also save trace files that you can use for both Sysdig and Sysdig. Let me show you a demo of about all this thing work. So I have my system here. Let me know if the font is OK. We should have a couple of monitors. So OK. It's OK, the font right now? Okay. So when you launch Sysdig, you see something like this, which if you are used to htop, is kind of htop. So the top list of processes running in the system were right now ordered by CPU usage, but you can also order by memory usage, things like that, just with a click of the mouse. So this is the process view, but we have also other interesting views. For example, the container view is much more interesting in a container-based environment, because usually in the process view you see tons, for example, of Apache instances. Here you can see there are tons of Apache instances, but from here we don't understand which Apache is running where and what is doing. Instead, with the containers view, we are able to understand what our stack is doing here. We have a MySQL database, some WordPress containers, and Nginx proxy, so we can guess it's a WordPress stack. With Enter, we can go inside a container and see the process view, but of a single container, so there is way less noise inside here. And while we are in a view, we can change it, keeping the same context, and see different data. For example, now we are inside this WordPress container. If we go in another view, like the connections view, we are able to see just the connection of this container. We are segmenting the data to see what we need. And all of this is done without running anything inside the container. So we are seeing this from the outside. We have other kind of activity we can see. For example, this is the errors view, which groups the system calls by the error return. For example, here we see a lot of inoent, which if you're used to low-level programming, it happens when you try to open a file and it's not available. For each row here, we are able also to see all the Sysdig events that are grouped there in this visualization. Just pressing the dig button, we are able to see all the events that generated this inoent error. And for example, here we can see that Apache is trying to open a bunch of files that are not available. This thing is just how Apache works. All of these features are available also reading a trace file. So reading a trace file, we can see what was running at that time, and with all the features that we saw. So for example, I can go again the containers view. I can dig into a container. I can go to the connections table. And also we have another feature called the echo, which displays the data exchanged. So for example, here we have a connection. If I press echo here, I can see the HTTP transaction run inside this connection here. So the request and the response. So this is Sysdig, and as you can see, is pretty simple to get something meaningful for all this fine granularity data we have. Then let's go to the command line. The command line, if you run it just as it is, all the system calls are printed on screen, which is not so meaningful, but the power is on filtering and on running Chisel. So, for example, if I filter by container image and I put WordPress, now I see just the events generated by the container image WordPress. And I can also tell Sysdig to write the container context. So here I can see all the WordPress containers that are generating this activity. I can also improve the filter, like add sock family equally p. So now I'm seeing just the network activity. And here we are still on low-level stuff, right? Just the system call. But with Chisel, we can leverage this data to have the data that exactly we need. For example, here there are a lot of HTTP transactions. I don't care exactly about exact system call. For example, I want to see all the requests coming. We have a Chisel that is called HTTP log. And when you run it, you see for every line an HTTP request or with the response code generated with the URL and things like that. And this is done from our Lua script analyzing all this data. So with Sysdig, you can go from low level to high level very easy without having to know deep level stuff like kernel tracing or C++ or things like that. So that's Sysdig, and the goal of this session is mainly the hands-on. So we'll have a couple of exercises to do, and I'll help you to do them. But first, if you have any questions, I'll be happy to answer. Okay.
Once again, we have the mics if there are any questions. Also, during this hands-on lab, we've got a number of Sysdig folks all around. If you need help at any point, just raise your hand and someone will come over and help you one-to-one.
Okay. So first of all, you need to install the Sysdig. For sure, I hope you have done already. And download the captures we made for these exercises that are available on this address. The first exercise is on the trace file numbered 1. And in this trace files, you will find some weird activity on the machine because someone is trying to log into. And your goal is to find what he is doing and maybe find his IP address. So I give you 10 minutes, something like that, and to get into this. And after we will walk to this a possible solution. Cool. Mm-hmm.
If you get stumped at any point, don't hesitate to raise your hand. Someone will come over, give you a clue in the right direction.
Okay, few minutes left for this exercise. So if you have you are stuck from something, just raise the hand or yeah. Okay. Ah, okay. 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 Okay, so who was able to find out the IP address of the attacker? Oh, cool. So just let's see how how we can troubleshoot this. We said that some network activity it was there to there's someone trying to log. So let's first of all expect network activity using the top cons Chisel, which reports all the connections, all the top connections. But yeah, there is a lot of HTTP traffic there. Let's just focus on the SSH port, so the 22 ports. And here we can see a lot of traffic from this host, 10.1.1.123. Which is kind of weird because if you need SSH, you just run a single connection, not too many of them. So there's something weird here, and how we can expect the traffic here. It's not so feasible because SSH is encrypted. So let's see if meanwhile SSH printed some logs about what it was doing. So we have another Chisel, which is spy syslog, which, as the name says, just prints everything that is logged on syslog, and let's also filter by SSHD. And here we can see all the logs, and there is some some invalid user activity. Many different users name tried by this host. So it looks very likely that he's trying to do a dictionary attack. And yeah, so this is the culprit here. Yes, it's this one. Are you able to see it, or I can show in the slides? So mainly here we used the top cons Chisel and the spy syslog Chisel. Any questions about this? Okay. So let's go to the next one. Here there is another trace file, 02. And here there is a filing HTTP request. And the goal is to find the filing request. But bonus point if you're able also to understand why is failing. So what's wrong in this failing request. So go on the 02 file and do this. For sure, you can leverage something that I already showed you. So we talked a lot about HTTP. So yeah, you can leverage that.
Once again, if you need any assistance, just raise your hand. Someone from Sysdig will be around to help you.
As a hint, I suggest you to leverage the HTTP log for sure that I showed you. You can, there are plenty of requests, but yeah, with some grep you can find the wrong one. And then it's better to get into the single request and see, yeah, what's happening.
What's a good starting point?
If you are in Sysdig, then it's more, yeah, you should try to see the connections on, yeah, and on the HTTP ports and see what they have inside. So, have somebody managed to find what's going on? Yes? What was the culprit? What? WordPress? Nope, it's more something related to the configurations of the software, not like application level, like WordPress. It's more, yeah. Yeah, that's it. Yeah.
All right, Starbucks gift card for you. Well done. Well, can you repeat it?
Yeah, the issue is that the host header was wrong in one of these requests, and let's see how we can troubleshoot this. So, as I mentioned, it's a good point to troubleshoot the HTTP to use the HTTP log because you have all the log of the request happening. So you can easily grep by code equal 5. And you can see there are 2 requests filing. And once we have this request, we can inspect the traffic inside and see why they are wrong. So with Sysdig, let's open it. Okay, so let's go to the containers view. Our entry point for HTTP is the Nginx proxy. Inside this container, as I mentioned, we can change view and keeping the same context. So if now we go to the connections view, we see just the connections happening inside this container. There are many of them. Many are with these 172 addresses, which are internal of our environment. But the request wrong was from, there was mentioned another IP. Let's go down if we find it. At the end we can see there are these requests coming from the outside. Let's go with echo inside them to understand what's going on. So with F5, we can see the exact request and response. So this one is working well. We can see a 3002 response code, which is fine. And instead, let's go with the other of these hosts, the .17. Here, we can see that, this is the error request. If we see the diff between this and the previous one, we can see that the host entry is different. Here, it's using the IP address of the server. Instead, in the previous one, it's using WordPress. So there is the client using the right virtual host to in the request, and Nginx is not configured to answer in the using the IP address of the host as a virtual host in the HTTP request. So the host header was wrong, so we should tell our client to change it. So this is the HTTP troubleshooting here, which you can see, Sysdig is pretty useful to troubleshoot this stuff. Also, we did this offline, and it can happen, for example, as I mentioned, if you receive this an alert, you can see the request going on and troubleshoot them. As an exercise, this is more it's aware behavior happening in the system, and I'll tell you after some explanation about this. But First, let's see if you can figure it out why there is a script run that generated a weird syscall behavior. And I'll suggest you to go as a hint to the Sysdig errors view. And the first point is understanding what this behavior is about. And yeah, if you're also able to figure it out why this process is doing this stuff. Yeah, go ahead.
Assistance. Sysdig folks will be here to help. This is your last chance this morning to get one of those caffeine cards from Starbucks, so use the help.
Okay, so have you been able to find out something about what's happening in this trace file? Nobody? Yeah, go ahead. Yeah, yeah. There are tons of close events, and yeah, let's go on this and see what's happening. So if we run the top system calls Chisel, we see something weird. We have some syscalls that have like thousands of them, and close instead there are 1 million close events, which is very weird, right? If, as I mentioned earlier, if you go with Sysdig on this, with Sysdig, all these errors are ebadf, which on the closed system calls means that the file descriptor is not is bad. It's not correct. So the process doesn't have this the file descriptor open. With Sysdig, you can go with dig and see which process is generating this. And in this case, we can see that is a Python script generating all these events. Let's go deeper and see these close events. So let's add as a filter proc name equal Python and event.type equal close. Seeing a bunch of events, we can see that there is Python is calling close with a file descriptor number constantly increasing. So it looks like it's trying to close all the possible file descriptor number. So it's yeah, kind of weird, right? How is possible is doing this? A curious thing, if you were able to figure out, is that this is a script, right? So maybe we are lucky enough to see the content of this script, because Python, to run it, needs to read it somewhere, right? So if we put procname.python and for descriptor.name equals contains script.py, and use the echo file descriptors echo on echo Chisel, we can see here actually the content of the script. So here we can find that this script is calling is creating a sub process, and this function accepts a parameter called close FDS, and this is called true. And with this parameter, this Python library tries to close all the possible file descriptors. Why is doing this? When you have a process that does exec, so runs another executable, the file descriptor opened are kept opened. So if the process is not aware of this, just starts to open other files, do other stuff, and the file descriptors are kept open. So it's a leak of file descriptors and a leak of resources. So as a safe thing, some libraries like this one, but also I found the same behavior, or for example, in Keep Alive D, they, as a safe measure, they close all the possible file descriptors, which it was working kind of well a couple of years ago when the max file descriptor number was, the default one was 1,000 and something. So 1,000 events are not so much. But recently, in the latest kernel, the default amount is like 500,000. So you can, there are tons of system call generated just to do this, which is very weird. And a best solution to do this is simply adding a flag when you open a file called cloexec, which means that the kernel automatically closes that file descriptor when exec is called. And it's way more efficient because it happens automatically done by the kernel. So yeah, this is the cool print here, which is a nasty troubleshooting behavior that I found out a couple of months ago, troubleshooting our stuff. And yeah, it was nice to share with you. Yeah. Thanks everybody to joining this hands-on today. I hope you liked it. And yeah, that's it.
Thanks so much, Luca. Luca will be around here in the session and in the break area in case you have more questions for him. I think we've got one question right now, which we probably have a moment for. Hold on one second.
Just real quick, could you show us, again, maybe so we can capture it on our phones, how you went and printed the script?
What, sorry?
How you captured the script being loaded and printed that out?
Yeah, exactly. I started the capture. Yeah, when I made this capture, I started the capture, then ran the script. So in the loading of Python, it obviously reads the script to execute it. So for this reason, it's available there. Yeah. Yes, I have it also here. It's in a more big font. So I used the echo FDS Chisel and proc name we equal Python as a filter, and fd.name contains script.py. Script.py is the name of the script. In this way, all the Python activities filter just to match this file descriptor. And with echo FDS, it's printed on screen. So, yeah.
Thanks again, Luca.
Yeah.
And now, please welcome to the stage one of the Sysdig originals talking about how to build a chisel, Gianluca Borello.
All right. All right. Good morning, folks. Today we are going to talk about two of my favorite topics ever. One of that is writing some code, and the second one is doing real troubleshooting from the fields. It's going to be a lot of fun. So we'll start by talking about extending Sysdig. I decided to talk about this because very frequently in the Sysdig community online or at conferences, people ask, Sysdig is very cool, but I would like it to do my own thing. I have this very, very custom use case, and I want to make sure that Sysdig can cover it. And we have never given a pretty, let's say, a very accurate answer. So I'm trying to address some of those points today. Let me start with a little bit of a deep dive inside the Sysdig architecture. As Luca said, you're already pretty familiar with the concept of the system events that are being extracted by the kernel. And this is a further level of zoom in inside the architecture. So Sysdig is composed by different modules. In particular, we have on top the Sysdig command line interface, or Sysdig, which is the one you have already used in these exercises. This Sysdig command line leverages a couple of very important important system libraries that we've wrote that allow to make all the magic happens. And then at the kernel level, we have this little kernel module that fetches all the system calls that happen in the system. So the nice thing about this architecture is that it's indeed modular, and depending on what you're looking to do, you can tap into each of these components to extend Sysdig with your very, very own and custom use case. I'm going to spend 5 minutes in digging down a little bit into all of this, and then we'll have a hands-on part in which we will create a Chisel from scratch following a pretty cool use case. So the first part is essentially the command line. Most people should heavily read the Sysdig man page and the Sysdig help section because the command line is absolutely powerful and flexible. It fully embraces the Unix philosophy, so it allows some very great details of customization so that then it can play well with your typical Unix pipeline of commands. So here I have a few examples. For example, as we have seen during this hands-on exercise, by default, Sysdig will print you on screen all the system events, and it will print you the time when they happen, the process name, the event, and then the arguments. But there is much more to it. In some cases where I'm doing some real troubleshooting, depending on what I'm looking for, I'm interested in looking at a very specific subset of fields that I might be interested in. For example, return type of the system call, or number of bytes that have been returned by my read operations because I'm debugging a slow networking issue. So if you use the -p, you're able to customize the output format of Sysdig. And in this case, for example, you can see how I am changing the default output format, and I am getting an output format that contains, for every container, the Kubernetes namespace where this event happened, which normally I might not be interested in the specific Kubernetes namespace. But depending on the troubleshooting scenario that I'm digging into, that might be very useful. It's a workflow that is pretty much borrowed from the network world. If you've ever done network troubleshooting with Wireshark, you will know that once you start digging into a troubleshooting use case, you will start filling up all your Wireshark columns by these crazy columns containing the is my TCP specific flag set or not, and you put them as a column because it helps you with essentially with the troubleshooting. Then we have other more advanced ways of essentially consuming the Sysdig output. One typical one is the JSON output that will just emit you a stream in JSON of all the events that are going on in the system. So you can use that one, and you can link that JSON output in your super fantastic web application that will show you a chart of how your system calls are slow, for example. And then, as Luca touched just now, I think the greatest ability for Sysdig is its ability to sniff into the I/O of the system. And if you use, for example, the -A, it will print you on screen the I/O buffers as they happen in the system in an ASCII encoding. If you use -X, it will print you the buffers that are being exchanged in the system in a hexadecimal format. And it's nice because then you can copy and paste that to XXD and, for example, reconstruct a binary thing. But don't do that just yet because the use case I have in mind is dangerously close to this one. So again, the command line can be explored absolutely, and it's very powerful. Then we have chisels. As you have seen at this point, chisels are really a super powerful abstraction that Sysdig exposes, and are really the first-class citizens for extending Sysdig. And again, chisels are little Lua scripts, very easy to write, that are automatically discovered by the Sysdig engine, and the Sysdig engine will feed to these Lua scripts all the events that come from the kernel, along with their full state. So for each event, you can look at the Kubernetes pod or the container where they were generated. And the nice thing about this is that the performance are very good, and you have full access to the whole Lua library, so you can really go crazy with use cases. We have been people from the community really coming up with very creative ways to extend Sysdig. And my use case will be pretty focused around that, as we'll see in a couple minutes. Since we are going to dig into the chisels, This is how a Chisel essentially looks like. I hope you can see it by looking also at the side monitors. This is a very simple Chisel in just a few dozen lines of code that counts how many system calls are being called and filters them by a system call argument that is passed as a parameter. So if you pass it open, this Chisel will count you how many open system calls have been called. And the Chisel is initialized with a bunch of boilerplate, which is essentially metadata that the user needs to specify in order for the Sysdig engine to discover the Chisel. And then the bulk of the action is done by these callbacks. These callbacks are the actual functions that the Sysdig engine will call you, essentially on your behalf, when there is an event ready. For example, you can see in this init section, we are using the Chisel API to ask to the main Sysdig engine to give us these two fields, evt.type and evt.dir, which are just standard filters in Sysdig. And we are essentially telling the Sysdig engine, hey, be ready because I will need those two fields every time you feed me an event. And then we have the core of the Chisel. The core of the Chisel is by far the onEvent callback. The onEvent callback is the function that gets called every time you get a single event. And in this case, you can see the logic is pretty simple. So we are just getting the event passed as the EVT local variable. And we are comparing the system call name with the one that we got as an argument. And we increment the counter if that's what we needed. And then we have the onCaptureEnd, of course, which is where we print the summary. We print the global counter that we saved. So for most use cases, Chisels are by far the stopping line. You should be able to achieve everything you want to achieve in your custom system monitoring, system troubleshooting tool by writing a custom Chisel. But if you really want, Sysdig has been designed, again, with modularity in mind, and so it easily can export all the underlying system libraries, and so you can access them. This might be a bit more advanced, so I'm just going to spend a minute on this. But the first library that we expose is libsynsp, that stands for System Inspector. Libsynsp is a C++ library that gets all the events that come from your kernel and builds a very powerful state machine on top of that, a state machine that wants to model the state of your whole operating system. In particular, the state machine contains a table with all the processes in your system. It contains, for every process, it contains the list of files, the list of network connections, the list of containers, the list of cluster orchestrator data. And this state machine is used when in a Sysdig command line or a Sysdig Chisel, you specify a filter so that we do the matching between a random event that comes from the kernel and its whole state. So when you see a write on a file descriptor number 5, the system call is in itself stateless if you just analyze it in its singularity. But if you look it up in the state, you can see, oh, this file descriptor 5 is var log whatever.log. Using Synsp is a little bit advanced, but is the best way if you really want to build a custom stateful system analyzer. And the interface looks like this. It's a very simple C++ program where you can see you're creating the Synsp object, and then you are opening the object, and then you enter in this while-true loop, essentially, in this event loop, where you're asking the next method to the inspector object, and we'll fill you a pointer to the next available event. And then, as you can see in the marked red line, once you have the event, you can look back the state of the system attached to that event. You can see that from the event, I'm asking the getThreadInfo, and from the getThreadInfo, I am navigating to the thread object, and then I'm printing the command line of the thread as well as the container ID. So if you start building around this state abstraction, it gets very powerful, as we'll see in 30 seconds now. The next library that you can tap into, and we get even more advanced, is essentially libscap, that stands for lib system capture. Libscap is a much lower level C API that is very similar to libpickup if you've ever done low-level network programming. It's mostly stateless, and its whole purpose is just getting the events from the kernel as fast as possible and feeding them to user space. So it has no state whatsoever. And because of that, is a very high performance. And it can be used if you want to build advanced system analyzers where you are doing your own housekeeping of the state. For example, a typical use case was the NTOP guys. I'm sure you guys are familiar with NTOP. A couple years ago, they had this very high performance network packet analyzer. But as Lori said at the beginning, once you start building a network packet analyzer, it's not easy to see which processes are attached to those packets, to those network packets. And so they were using the driver for capturing their packets, and they were using SCAP to just get a very thin subset of the system call in order for them to correlate which processes were generating which packets. And then they keep their own state with probably their super efficient hash table or something like that. So that was the perfect use case. Again, this is pretty advanced, so for the typical user, this is not needed. And this is how libscap looks like. So you can notice that there's always an event loop, but the API is now in C. You call the scap open function that returns you a handle. And once you have this handle, you can still get a pointer to the event, but the event doesn't have any state attached to it. So you can pretty much just see the arguments of the system call as if you were in strace. So for most advanced troubleshooting use cases, not very useful. So this completes a very quick overview of the internals of Sysdig, and I hope this answers some of the questions that people had about how Sysdig works. But then let's try with actually get something done, and let's try to really extend Sysdig. Since I'm a very lazy person, I wanted to try to find a use case that I could re-leverage in the community somehow. So I stumbled across this message that came on the Sysdig mailing list a few months ago, where this guy said, all right, I have a Sysdig capture from a server that was compromised. On this server that was compromised, the attacker did a wget to download a binary file. Of course, I don't have access to the server anymore because it has been tainted and whatever, but I still have access to the Sysdig trace file. Is there a way through which I can reconstruct that file? This is really the perfect use case for a custom Chisel. Because Sysdig, as you have seen, as Luca just shown you, Sysdig captures all the system calls and all their arguments, so all the I/O content that has been exchanged. So in this trace file, I will see all the activity that wget did to write that file on disk. So if I can just write a Chisel that can reconstruct that, I'll be set, and I will have this use case. So the Chisel that we're going to write is going to be called the scavenger Chisel, because it will essentially parse a Sysdig trace file or even a Sysdig live system, and it will scavenge all the I/O activity captured by Sysdig, trying to actually reconstruct the binary files that we have there. All right, let's jump into, finally, the action. Let's see. I'm trying to 4, 5, 6, 7. This should be probably big enough. If you guys cannot read in the back, also on the side monitor, just raise your hand because it's very important that you can see. So this is the trace file that I have. This is a trace file that I extracted from a very popular blog post that we did a couple years ago. It was called Phishing for Hackers. That was a pretty similar use case. And if you look at this trace file, now I'm reading the trace file with the spy user's Chisel, and I can see that the root user did a bunch of terrible things. He created a .tmp directory. It entered in the .tmp directory, and then it downloaded from this very dubious URL this file, rk.tgz. And then it extracted the file, rk.tgz. And of course, with the spy users, I can see what the user actually did, but I cannot see the actual content that was written there. So can we write a Chisel to do that? Yes, we can. Let's take a look at how the system events are happening. So without opening the Chisel, this is how the trace file looks like. I have a bunch of activity from bash, tar, gzip, wget, really a lot of stuff. And I want to focus on this part, which is the core part. This is where wget opens the file /root /tmp /rk.tgz, and it opens it in create and write only mode. So after the open, I know that the file was opened and written on disk. And now, after wget opens the file, it starts reading a bunch of crap over the network. You can see that it reads from this network connection on port 80. It starts reading this payload. You can see that this pretty much is a binary payload because it's not showing up that well on the standard output. And this crappy payload is just taken verbatim and written in another write operation inside the file, root.tmp rk.tgz. So what if I write a very simple Chisel that keeps track of all the opens that are being done and keeps track of all the writes that are being done to a file, and instead of printing the output on screen, it saves it in a local file so that then I can reconstruct what actually happened in my compromised instance? Turns out, yes, I can. So I'm going to split the screen over here. And let's start by writing a Chisel. Writing a Chisel is really as simple as creating a Lua script in your home Chisel directory. And here I already put some boilerplate. I already put the description and the name and the category. So now if I do sysdig-cl to list all the Chisel, I can go into the IO category, and my scavenger Chisel will show up, right, with the description, scavenge everything. Of course, if I run this Chisel now on my trace file, it won't show me anything because there is no logic. But turns out the logic is extremely, extremely, extremely simple. So let's actually implement it. A Chisel starts with the function onEvent, as we said. That's really the basis of it. So if I just do function onEvent, this will be the whole body of my Chisel. So the first thing I can do is, I know that I'm interested in the open events. So how about I get the event type? Create a local variable, eType equal event.getType. And then I filter over here if eType equal open. Actually, also need the open at because tar was also doing the open at, as we'll see. Then let's start printing something. Let's build this very calmly and putting a lot of printfs while we iterate. And we can do opening file, end. So if we now run this Chisel, we start seeing something slightly more interesting. We start seeing one line of opening file every time a file is open, right? The next thing, right, at some point we need to know the file name because just knowing that a file was open doesn't help us because I need to understand which files were written. So how about I just ask to the Sysdig engine, hey, give me the file name for all those system calls. This is as simple as asking to the Sysdig engine, request field fd.name. Again, I'm asking the name of the file descriptor. And then I'm going to actually use this field for every event. So local name equal evt.field fname. Now I have in the variable name, I have the name of the actual file name. So how about I concatenate this over here, .name. And if I run it again, oops, let me put as a filter just the exit events because I'm just interested, I don't want duplicates. Now I start seeing something interesting. I starting to see all the files that were open. And of course, I also have over here the rk.tgz. There we are. So we are already doing progress. Now, the next part is, of course, let's intercept the actual I/O activity. So let's intercept the writes. And once again, now you should know how it works. So over here, I can just put otherwise, if the event type was a write, then print write file name. And so now I not only see the files that are being opened, but also the writes operation. And let's keep iterating over this. We have the file name, we have the writes. Now we need the content, because that's really what we care about, right? The content is super easily available in Sysdig because every write operation has the data field that contains the full binary payload that was extracted by the kernel. So let's ask to the Sysdig engine the data content, fdata, chisel.request field. The data field is under evt.raw argument because I don't want Sysdig to mess up my binary payload with its encoding since I'm going to be stored this verbatim on my system. And then I can ask for local data equal avt.field data, right? And now, once I have the file, I can not only print the file, but I can also print the content data. And if I run this, right, F data, thank you. And if I run this, of course, it will print me a bunch of crap. I'm sure we can also find some nice emoji in these characters, because that's really not what I need, right? I need to redirect this output on my disk. So how about I start defining a strategy, and maybe I can keep, this is very basic scripting skills. I can just keep a table in my Lua script, a key value sort of table that as a key I put the file name, and as a value I put a string that I append, and I append every time to this string all the content that comes from the write. And then when I see that the file was closed, I just flash all this on disk. This is really, really simple. So let me just do it. So let's create a table over here, files. Creating a map in Lua is super simple. And when we open a file, we just insert files as a key name. We insert an empty string, because of course the file has just been opened. But then, when we actually need to write and we have the data, we just look it up. If file's name exists, because we don't want to save a file that has not been opened during the duration of the trace file, then I can just fetch the content, file's name, and I can put in the same table, file's name, I can put content concatenated with data. Super easy. Let me comment this stuff because we won't need it. And this does really pretty much everything that there was to be done, except that now we need to actually save the file. So to save the file, let's just intercept the close, and let's make sure that whenever we see a close, we serialize whatever in the map we had for that table, for that file name. So over here, else if etype equal close, then let's say if we had the file in memory, then content, file's name, and let's also do if the content len was not empty, because otherwise here we would also intercept all the read activity. Then let's just print scavenging file dot name. And after this, we will start saving the file on disk. So if I run this now, I get a much more interesting output that contains really just the files I was looking for. Scavenging file, with all these, you can see that this is all the files that tar wrote on the disk, because not only I'm intercepting the activity of wget, but also the activity of tar when it extracted the file. So now let's close the loop. And this is really as simple as, instead of printing just scavenging file, let's save it on disk. In Lua, this is super easy. So let me actually do one modification. You can see that here in the files I have all the slashes. So whereas I want to save them in a flat structure in my local directory, so I'm just going to change the original file name, substituting slashes with underscore. So I can do file name equal string.gsub name slash underscore, just some little boilerplate. And now, again, we keep going on with the boilerplate. So in lieu of writing a file is as simple as doing opening a file pointer, io dot output, file name. Then we do io dot write content. And then we do io dot close file pointer. Super easy. Now if I run this, I get the same output of the script. But in my local directory, now I have all the files. All the files that my Chisel scavenged, even if the server was compromised and was long gone. And these are real files. Look, if I do file star, I see the actual file type. So I can see that I have rootkit.tgz. And it's a tar archive that I can actually inspect. But turns out I don't even need to inspect the tar archive, because tar, my attacker already decompressed it with tar. So I can just look at the actual thing. And look, I have a bunch of binary LSOF that are actually Linux executable. But let's find, just for the sake of it, something more interesting, something that is ASCII readable, right? So for example, this setup script is a bash script. And just to prove you that I was not fooling you, this is really the actual script. We can amuse ourselves into reading it. We can see that this script was written by me, very informative, and is private to do not distribute. It says, do not touch below unless you know what you're doing. Before we move on, let's move on to a safe ground. It even has some rainbow colors. Very nice of the attacker. And it apparently does a bunch of unzipping shits. And I mean, I read this whole script, and this guy, the attacker, should have been a great comedian. Like, the messages he wrote are amazing. Look at this. So patch manually and fuck off. It even contains a typo. So anyway, this is a rootkit, and what it does is a full shell script that does a bunch of health checking, and then it will start replacing all my system binaries inside the system. You can see how it will start replacing TTY load, it will start replacing netstat, it will start replacing PS, it will write a bunch of stuff in my init tab, and there you go. So, and here we have the full file, because if I go down at the very last end, I can actually see the EOF in the script. And I can also see that there's even an email address, so we can maybe get in touch with the attacker, although this was very old because it was 4 years ago. Yeah, so we have been able to reconstruct any file, and this file was in ASCII, but the next one will be, but the other tar file was binary. And so with Sysdig, look at how in just literally 37 lines of very simple code, including also the printf. Let me remove it because I don't like it. So in 35 lines of code, we have been able to achieve this, which is a pretty cool use case. And of course, this is not as thorough as it should be, because I did a bunch of assumptions, because there could have been a snap length for the buffer. So the actual script, if you go on GitHub, it's like double that size. But you will still see how in just 10 minutes, we have productively created something that has real value. And in fact, mangling with the I/O has been the biggest use case for people writing their own chisels. I know of people who have their own binary protocols for their application, and they wrote a chisel to actually dissect it, because it was easier than doing it than other instrumentation platforms. And this is really the testament on how simple the API is. And as long as you have good data at your fingertips, then you can get all this stuff done. This concludes the talk. In my next one, we will go a bit deeper into advanced troubleshooting use cases. But this was the first part. I hope you liked it.
Gianluca, thanks so much. We're running a little bit late, so we don't have time for questions, but Gianluca is going to be around all day in case you do have some follow-ups for him. And now our next speaker, one of our prized guest speakers, please welcome to the stage Senior Performance Architect at Netflix and eBPF fan, among other things, Brendan Gregg.
Can you turn off mine?
Today, my name is Brendan, and thanks for having me here. I thought you could talk on designing tracing tools. Still not on. We can't hear you.
Yeah, mine is still on. Can someone turn?
Part of using a tracer, however, is what to do with these superpowers. I've given many different talks where I've discussed issues that we can solve with different tracing tools, methodologies that we can use to apply to using tracing tools. In this talk, I wanted to do something different, where I will cover how I design tracing tools and how I build tracing tools, as that may be another way to help you see how to wield these superpowers and how to apply them. Sometimes when I create tracing tools, people see them as though I'm the one with magical superpowers, the way I can create them and present insights into the system. But in this talk, what I want to do is dispel some of that magic and show that it is a routine, a set of steps that I go through for creating these tools that we can all do. I'm still developing tracing tools, so I'm currently developing them for BCC and BPF. And some of these tools I've developed for many different tracers in the past. Some of them are new, but I still have my hands on tool design. This talk will be interesting for tool developers if you end up actually designing and building tools. But it will also be useful for everyone who consumes tools. So the problem with tracers, as I mentioned, is what do we do with these superpowers? And by seeing the sort of things we can do, you know the sort of things you can ask and the sort of things you can expect from application performance monitoring systems. What I'm going to cover is applicable to all tracers. So whether it's Sysdig, BCC, BPF, DTrace, System Tap, LTD&G, I've used far too many. I've used all the tracing tools. I'll start with methodologies. And this is where I really start with coming up with tools. It's easy with a tracing tool to print out numbers. But is it useful and is it solving real problems? With methodologies, these pose the questions of the system that we would like answers for. And this is really the genesis of why I come up with tools. For methodologies, I like to start with a functional diagram, a block diagram of the system. I've got one here that shows the kernel and application, so classical operating systems block diagram, but you may have one for the internals of your application, your distributed system. Then based on the functional diagram, I can apply methodologies. To give you an idea of how this works, I've discussed it at the system call layer, and Adam gave a talk earlier today about the importance of syscall tracing. And so here's 3 methodologies that I could apply to the system call layer and how they could become tools. Workload characterization. With workload characterization, I don't care too much about the resulting performance or the resulting errors. I just care about summarizing the load that's applied to the system. You'd be surprised how many performance issues are solved just because the workload is dumb. The application is doing millions of failed closes like we saw in the last lab. And once you identify that, you can then eliminate that dumb workload and improve performance, sometimes by factors rather than percents. So in terms of tracing tools, some examples I've done in the past include exec-snoop and OpenSnoop, which are really simple workload characterization tools at the syscall layer for doing tracing execs so that you can see when new processes are created and exec themselves, and OpenSnoop to see what files are being opened. Connect and accept, just seeing what connections, you can trace them at the syscall layer or higher up in the stack. And I've done tools in the past for that, which can be useful to understand network connections that are going on. Read and write size histograms. Why might they be useful for workload characterization? I've had issues in the past where you can see that you're doing far too many reads and they're very small reads. Maybe they're 1 byte reads. And you can change the application to use a larger buffer size and improve performance. Again, this is characterizing the load applied to that target, and that target is the system calls. It doesn't matter whether those 1 byte reads are fast or slow, or whether those failed closed syscalls are fast or slow. For this methodology, it doesn't. It just matters about identifying the workload. Then there's latency analysis tools, and that's a different methodology, and that's where I want to thoroughly understand the latency. And I've written many tools like this, func latency for doing histograms. Maybe you want to do read and write latency at the syscall layer. Another methodology I like to use is one I created called the use method. And that's where I look for 3 metrics in particular: utilization, saturation, and errors. And so you can imagine coming up with a tool a tracing tool that measured those 3. It's very easy to create tracing tools that measure far too much, and you have too many numbers for the end user to understand. One of the beauties of the use method is it just picks 3 that are really useful, and then the user can understand those 3. So utilization is over time how busy that resource was. Saturation can be a measure of queue length or time waiting queued, and then errors are errors. And so I should write a tool that does network utilization by thread so that you can imagine doing this in Sysdig or any tracer where you can expose what percentage of time does this application thread spend doing sends, network sends, or network receives. Maybe it's already been done. System call errors is another use method style tool that you would think of doing if you're applying the use method to the syscall layer. So you can imagine doing those methodologies at other targets as well. So you can imagine going to the file systems layer and looking at workload characterization for file systems. What are the different file system operation types we do? So reads, writes, opens, stats, mkdirs, and so on. Latency. What's interesting there? Well, file systems can do things synchronously and asynchronously, so maybe you want to understand more the synchronous latency calls. And then for a use method of file systems, well, you could come up with errors. That one's easy, but you also may come up with interesting metrics to expose, say, utilization and any measure of saturation in the inner workings of a file system. So I hope that illustrates a little bit a methodology to pose questions that you then want to answer of the system, whether it's workload characterization, latency analysis, use method, or many other methodologies. It's too easy to get into the trap where you've created a tool, a solution in search of a problem. So I have some output, and I think, wow, that looks really interesting. Look at all those numbers, but I don't know what I'm going to apply it to. And so that's why thinking about methodologies first will begin with the questions. So to see this actually applied, I'll start with CLI tracing tools, and then I will do GUI tracing visualizations. And for the command line interface, there's 6 different templates I use. So at this point, we've got a methodology. So say I want to apply workload characterization. Now I've got one of these templates I can pick to create a tool. Now I want to talk about CLI tools for a few reasons. One of them is they have lots of uses other than solving a problem. Let me demonstrate. It should come back in a second. So earlier today, we saw Luca gave a Sysdig workshop, and it involved a lot of using Sysdig. So this is a text-based GUI. And then Gianluca did more of the Chisel style at the command line. Now, I really like the command line tools that you can run. And if you want to use an interactive tool like Sysdig, that's great. But I thought I would make the case for the value of the single-purpose tools at the command line, as I'm going to go through those in the slides anyway. And I thought of this during the lab. So I'm going to cover 4 reasons why I like to use the command line versions of this. So here's the Sysdig lab. Now I can run, so here I'm playing around. So I've got my trace file, trace03. I can list all the different chisels I can run on it, and I can run the top cons. Okay, I can run spy. Do I want to do a spy or top HTTP? How about the HTTP log? That's pretty good. I can do spy users, see what users logged in. These are all in my scrollback buffer. Okay. If I run a few of these chisels, what I can do is I can scroll back and forth, and it's in my scrollback buffer. So if I'm conducting an investigation, and I start off with a summary where I've got here's my top processes that are doing networking, and now I want to look at some of the HTTP requests that they might be doing, I can scroll back and forth and maybe associate a clue over here with a clue down here. That's something that lends itself very well to the command line with the scrollback buffer. A second thing I can do here is, if I see something interesting, this all may be obvious, if I see something interesting, I can copy and paste it, and then I can share it with colleagues. I can put it in say I'm using Jira to file issues. I can paste it in there. That's also a little bit more difficult to do with, say, a GUI, like Sysdig, where you're bounded to the screen size. Not that it's bad, it's just a different way of doing it. Another way it's useful at the command line is I can type history. You can see me mucking around. And if I end up solving a problem, I can then copy and paste all of the prior commands I did, and then include that in the Jira ticket or share that with colleagues as a learning exercise. If you're hopping around with Sysdig, it's really powerful and really great. But you can imagine thinking, how did I get here? Did I do function 2 and then went to this view and then I went to this view? Here you've got your entire history in the scrollback buffer. I can copy and paste things out, and I can type history, and then I get that summary. And then the last thing you can do at the command line, and Jean-Luc mentioned this as well, is you can bring to bear other Unix tools. So I was outputting things. So here's an output file. So here I'm doing looking at the network connections and exactly what was sent and received. And I was doing things like, let's grep for the 502 errors. Oh, there weren't any in there. Grepping for the word error. I can output it to a file. I can run awk, sed. So I can bring to bear a lot more tools and do some more ad hoc analysis. I can also do, while I'm here I noticed, I can do spectrograms. Notice the way I'm doing it, I like to put the chisel at the end, because then I can go up arrow, control W, and then just type in a new one, like subsec offset. And it's just quick in terms of keystrokes. Subsec offset is a chisel I added a while ago, or it's probably been improved since then. It's really nice to just be able to run it. Pretty cool stuff. So I'm going to go through some commands that are like that. You run them at the command line, and by running several commands, you can build up an investigation that's in your scrollback buffer, and you can refer to and copy and paste. So the first template is per event output. Sometimes the tool I'm creating, I would like it to have a per event, a total dump of all the events that happened, and then I can look at it later. That's good for workload characterization. I can also feed that into other tools. I might be grepping for things or frequency counting things. There's an example, OpenSnoop, which I've implemented many times. In fact, in Sysdig, it's a one-liner, just to show what files the open system call is operating on. You'd be surprised at how many times I've done this and solved a problem, because an application is looking for a config file in the wrong location, it's trying to open something in the wrong location, and you can see it straight away. A similar tool is filtered event output. This time I want to see per event, but only if it's based on some filter. I find my slower tools really useful. So I have things like file slower as a Chisel, which will only print, I think I borrowed the older version, it will only print events that are slower than a provided threshold. So only show me file access slower than 1 millisecond. And I've also done these in other traces for, say, the ext4 file system and ZFS and Btrfs and so on. Great for proving and exonerating performance issues. Some people say, my application's slow because I have slow disk I/O. I can run file slower and immediately prove whether you have slow I/O that's causing application pain. Interval summary is another template that might be a little obvious. So tools like VMstat and IOstat do interval summaries, and we can do them in tracing tools as well. And I saw there are some Sysdig chisels for this, for doing, say, network throughput, and it'll do the summary. It's another template, and it can be appropriate for the tool at hand. That one is a tracing tool that's doing the directory cache stats, so references, slow, misses, and so on. Count summary is another template I use quite often, and that's for looking at a frequency count based on a key. That example, I'm using func count, and I'm looking at the functions that began with VFS, and it's just doing a kernel frequency count. We saw some of them earlier today for Sysdig as well, and on the third lab, I'd solved it using the top syscall Sysdig, so that you could see that the closed system call was called the most. But it's just another template, appropriate for the job. There's histogram summaries is another template I'll use. And that's where I'm interested in the distribution for a metric, usually latency. And I've done these many times before. That's biolatency. That particular example is has a normal distribution, but often these are bimodal, which is quite interesting to know. Then when you want to see the histogram over time, you can use a heat map or a spectrogram. And so that example is from Sysdig, and that's where you can imagine a histogram, turning a histogram into a single column or row of colors, and then picking the color saturation, including the hue, based on the value. And this is great because I now get to see how the distribution changes over time. This is the sub-second offset heat map or spectrogram, which is one I created, which is very strange, but it has a purpose. What it does is it shows when events happened in the offset of a second. And so you can imagine I'm drawing a row for each second. If I'm looking at a particular event, I can see, did it wake up at the same time every second? If so, I would have a vertical stripe. Did it wake up, do a little bit of work, and then sleep for an entire second? But then, as time goes on, wakes up at a progressively later offset of the second. And you can see those diagonal lines happen in that case. What if an application woke up every 5 seconds? We can see the 5-second dots as well. Interesting visualization. Gives you an insight into how application timing may be working, and also of the arrival distribution. Does work all arrive at once? So whatever this workload was, a lot of the events would happen in one large group, and then we'd go to sleep for the rest of the second, and then wake up again, and that would slide over time. So those are the different templates, and I'll put these slides on SlideShare. Now, about creating the tools, I've gone through some methodologies to think about posing questions, templates for creating different command line tools. Now I want to talk about the style and decisions for those. I like the tools to be valuable. So I've created these tool diagrams in the past for Linux, which are fairly popular, but it's something that I do study a lot of. What is the current landscape for Linux performance analysis? I end up using all these tools. I'm a bit of a tool nerd. And then by understanding that, I also know what doesn't exist. It's very easy with tracing tools to reinvent the wheel, since there's so much information. If the kernel already has some counters built in, I'd rather use those because they're probably going to be cheaper than having to fire up a tracer and do it. So know what already exists and what doesn't. Another aspect to describe is, or characteristic to look out for, is overhead. Tracing tools are often used, I'm often using them for performance analysis. Tracing itself can be dangerous. The overhead is usually relative to the event rate multiplied by the tracing event cost. Adam had a slide earlier today about how strace, the current implementation of strace, is violent and uses breakpoints and can really slow down an application. As an example, I've got how Sysdig works. The Sysdig driver creates a ring buffer so that our Lua chisels can asynchronously read at a much lower event rate, much reducing the overhead of this. And so times I've tested it, Sysdig is like 20 times lower overhead than strace. But there's still overhead. And one of the challenging things about using tracing tools is having a good feeling of what the overhead is going to be, and when it's safe to do something and when it's safe not to. You get pretty good at knowing the frequency of things. For a lot of tracing tools, if you're, with the exception of like strace, if I'm tracing something that happens at less than 1,000 times a second, the overhead should be negligible. If it's less than 10,000 times per second, it may be pretty hard to measure. If the event rate is over 1,000,000 times a second, I'm probably going to be able to measure that overhead of the tracing tool. So you get an idea of what has different event rates. If it's disk I/O, unless you're a storage array, disk I/O shouldn't have a high event rate. And you can use IOstat just to double check on production servers. So maybe you're doing 100 I/O per second on a server. That's going to be negligible to trace. File system I/O, that's going to be a lot higher, as your application will often hit out of the file system cache before it gets to doing disk I/O. And so it's something you might want to check, but if I'm tracing file system I/O, maybe that's doing 1,000 events a second, 10,000 events a second. It depends on the application. And that can get into the territory where the overhead will start to cost in a measurable way. Scheduler events for the kernel. So every time the kernel does a context switch, that can have a really high overhead. That can happen over 1,000,000 times a second. Per packet events. Would per packet be high or low overhead? What do we think? High? If I'm doing per packet. Per network packet? Some people. What about low? Who's up for low? Nobody? It depends on the application, but packet rates can get really high. So if you're on 10 gig networks, you can easily get to 1,000,000 packets per second. That's actually something that's valuable for moving closer to the application. If you trace at the TCP level, the event rate can be lower because TCP is operating in buffers, which then gets split on MTU down into the packet size. And so times I've tested, I've had a 3x delta between the packet rate and the TCP event rate, which means it's cheaper to trace at the TCP event rate. If you keep going to the syscall layer, it should also be cheaper, which is what, say, Sysdig does. Your application may be doing 1 megabyte writes to a network socket, but at the packet level, it has to split them into 1,500 sized MTUs. So you can imagine any tracer where you're operating at the packet level is going to have much higher overhead than if you go up stack and go to, say, the syscall layer. It's these sort of thought processes that will help you design good tools. Think first and foremost, what is the frequency of events I want to trace? And also to look for, is there a way I can solve my problem with a lower frequency event? So as an example of that, recently I wanted to know the the throughput of TCP sessions on service. And so I initially started by tracing send receive, TCP send receive. Not as bad as packet send receive, but then I found out I could do the same by just tracing TCP set state, where it's the change of TCP session state, which is a much lower frequency event. So when you're changing from, say, SYN receive to established or established to last stack, and then I can actually pull out throughput statistics from the kernel. And so I've gone through this iterative process of I can do send receive, but how can I make this faster and what's a lower event rate? You can actually imagine doing that at the syscall layer as well, where maybe I can do this just by doing the connect and accept and when we close that file descriptor, instead of having to touch send receive and read and write. I also say design for low overhead and document expectations. And so a lot of my tools nowadays, I will, in the man page, have a section on overhead and just state clearly, this is what the overhead should be. You may have a tool that does have a high overhead, so long as you warn people about it, they can operate with that. Like my strace one-liners, slow the target process and do this. Documentation. I think good tools have 3 docs: the code comments, a man page, and examples file. So the code comments, obviously for the next person who's reading it, a man page is a nice way to summarize what the tool does, to have a synopsis and an abstract, to talk about columns and switches, and then an examples file to, I really like examples files. People learn tools often by looking at screenshots, and this is also a testament to tool design. If you design a good tool, then I can look at the screenshot and then I can understand what that does. And so a lot of the tools I create, I will deliberately create a text file of example screenshots because I know it's a quick way to learn what the tools do. And in fact, I've probably got some of them sitting around, like, so my BCC tools. So it's just a text file that says, this is demonstrations of this tool, here's some output, and then completely explaining it so that if someone's really new to this, then I haven't left a detail out. And just going through examples and examples and examples. So I'm a big fan of, this is one of many toolkits I've created, and I've got tools, and then I've got example files sitting next to each other. Every tool I write has an example file and a man page. Concise, intuitive, and self-explanatory. It's nice to have tools that don't have any clutter, don't have any unnecessary detail. Here's an example I like, I/O latency, and it only says what I need it to say. There's no wasted text. It's also intuitive. It's showing me a distribution, and it says that. It shows columns are labeled, so millisecond ranges. And I've got this sentence at the start, tracing block I/O, output every 1 second, Control-C to end. So the output is self-explanatory. You know what the tool is going to do. When I'm creating tools, you can also think of how would they look if these were in a textbook or if these were in a slide deck. Is there any wasted space? A lot of my tool outputs, they're very easy to put into slides because I just stick to the exact content necessary. I also follow Unix philosophy to do one thing and do it well. And there's a case for multi-tools, and I've written some multi-tools, but I also like to have the single-purpose tools. I mean, you can think of OpenSnoop as a pretty single-purpose tool. It just traces open syscalls. ExecSnoop is another example of a single-purpose tool. I also like to make sure the output is less than 80 characters wide. And this is something that I'll fight over very fiercely. It's not just because that's the minimum size of terminals. With the output, in terms of helping tools get adopted, people will put your output in slide decks like I have, in books, in blog posts. And if you have that tool that has the 130 character wide output, it actually causes everyone a headache. Like, maybe that fits, but maybe it's going to cause problems when people are formatting it. It just makes life a lot easier if it's unnecessary to make it that wide, make it fit within 80 characters. And then that screenshot can get copied and pasted around a lot more. POSIX style arguments. I really like my tools to have arguments that follow the same theme. If a tool does one thing and does it well, but I don't have weird arguments that completely change the behavior of the tool. And so here's biolatency, so I can add timestamps, I can change it to be queued times, I can change the units, but that's about it. You can imagine a tool. It's pretty easy when you're writing these tracing tools to say, well, the tool can do summary output, but I can have a switch and it would do per event output. And I find those tools more complicated to use. I like to keep them separate. So if you have a summary tool, it's a summary tool. And if you have a per event output, it's a per event tool. We've seen some of this today with the Sysdig tools, how there's clearly summary tools like top, prox, net, and then there's the per event output tools, which I think is good design. Also, think about the arguments and what would be ideal. Like, when I design tools, I really sweat very carefully about getting this as perfect as it possibly can be for tools that I'm publishing. So if I'm running a tracing tool that I'm going to use internally, and it's a hack, but I need it quickly to solve a problem, that's okay. But if I'm publishing it to share with other people, I really want it to get it perfect. And for there not to be a single character out of place in the output, or any dumb option, or any unnecessary option that makes it more difficult to learn. And one way to think about this, I guess, is the ping command. And some of you may know this story. Mike Muss, who developed the ping program, did it in one night. So he saw ICMP had echo request and echo reply, and thought, wouldn't it be cool if I could have a Unix tool that did this to find out whether another machine was alive or not? So he wrote it in one night and then shared it, and he later said if he had known that ping would be the greatest accomplishment of his life, he would have spent more than one night developing it. He would have added a few more options to ping, right? He said he was insanely jealous when a little later on, Van Jacobson did spend some more time on that, and Van Jacobson realized the trick of incrementing TTL so that as they expired, he could come up with a traceroute program. So if Mike Muss had actually stopped and thought about ping for a few more days, it may have actually had a traceroute option, and these wouldn't have been separate tools. Although it's probably a good thing they're separate tools because they do kind of do different things. But yeah, I try to think a lot about the tools and to get them really perfect. In my slides, which I'll share, I do have a table of POSIX-style arguments. So things which are conventions that I follow. Testing. I spend a lot of time testing tracing tools. I spend more time testing them than I do writing them. And I think if you can't write the workload, you can't write the tool. I do see from time to time people want to write a tracing tool, but they don't quite understand what it is they're tracing. And it's really illustrative to write that sample workload and to then trace it. So if you have a known workload, like if you can create a prime number of events and inject that, then you can verify the output of your tool to see if it matches. So maybe that's 23 events. Testing can be more time consuming than writing the tool itself. So I spend much more time writing these tools than testing these tools than writing them. Automatic tool testing is difficult, as a lot of the tracing tools, you may need cooperation with other hosts, network hosts, and coming up with a test bed to reliably do that where you can trace out the targets is a complicated problem. So I had some examples here. How are we going for time? I know we're running a bit late. What's the...
You got about 5 minutes and then a few minutes for questions.
Like 5 minutes, all right. So some examples here, but I've already had some example screenshots. So tools I like, get host latency, it's sparse, it just does what it needs to do. ext4 slower is similar to my file slower, where I give it a threshold, output fits within 80 characters, and it's a nice single purpose tool. And biolatency is an example of doing histograms, another nice concise tool. For GUI tracing tools, I want to quickly go through some visualization so that you can see how tracing tools can move to GUIs as well. For a lot of us, this may be where you end up spending more time using tracing tools, even if you realize it or not. So if an application vendor creates a performance monitoring tool that's a GUI and you're using that on systems, you may have no idea that behind the scenes it's actually using some tracer. So as templates to think about, similar to my CLI tracing tool templates, there's event logs. And that example is from Wireshark. So something we might be quite familiar with, Wireshark doing tracing at the packet level. There's tables, which is another template. This one's a bit boring. It's just my Google Chrome Task Manager. But you can imagine using a table as similar to my CLI summarization tool. Line graphs is another visualization template. This is an ancient tracing tool that actually used line graphs, a dynamic tracer from the 90s. But maybe that has a role for the GUIs you're building. Histograms, similar to what I had at the command line with the distributions. This histogram is bimodal, and that's really valuable to investigate and to see, say, tail call latency and outliers. And then heat maps, which we've seen many times today already with spectrograms. This is a heat map that Adam and I worked on at Sun, and this one's showing disk I/O latency over time. I really like this one. I was doing an investigation of throughput to a storage array, and to find out maximum throughput, I lit up 1 disk, and then 2 disks, and then 3 disks, and then 4 disks. And so I lit up the disks every few seconds until I had lit up all disks with load. And when I looked at the latency heat map, it looked like a pterodactyl from the Atari Joust computer game. And so obviously I had to get a screenshot. But really interesting to see what happens as we cross different points in that workload. Going from 8 to 9 disks is where the beak becomes the head. And I had a SAS engineer explain to me why. It's because, that's because it's handled in this way, and now there's contention. And so each of these characteristics has a particular meaning. I've had someone complain about the heat maps that I've done at a conference to say that by revealing all this information, I'm making more work for performance engineers because now we're on the hook to explain them all. But I didn't create the pterodactyl. It's always been there. You just need the tools to see them. And so that's why I like spectrograms as well. It's the same thing. There's waterfall charts. Just to include in my deck of visualizations for tracing tools. And that one's the classical looking at a website loading from its components. You can do directed graphs from tracing tools. And so that example is from Netflix, our SOLP utility, where we can see what microservice calls what other microservice. But it's a visualization that can be handy for trace data as well, whenever you have a hierarchy. Flame graphs. Flame graphs are simply a visualization of stack traces. Now, flame graphs are great for sampling profilers, but I'm talking about traces, per-event traces, and I use flame graphs to visualize off-CPU time. So off-CPU time is when you block on CPU and you wake up later. I can grab a stack trace that explains why I blocked, and then the time I was blocked. And so that example is off-CPU time flame graph for tar. You can actually see proportionally the time I spent reading from disk, reading directories, and so on. And then the last visualization is flame charts, which I wanted to mention differently. Flame charts are what's in Google Chrome DevTools. And they're different. Flame graphs have the alphabet on the x-axis, the population. Flame charts have the passage of time. And so if you're sampling stack traces or you're tracing the flow of something, you can plot that over time and see how it changes. So desirable attributes for GUIs, valuable just like the CLI tools, documented, and I think we can do a lot more of documentation in GUIs. Tested, real time, and dashboards is a big opportunity to support methodologies, and we do that at Netflix, where developers create their own custom dashboards to help step through a particular process of analysis. So I'll share these slides. They have my CLI templates, and they also have the GUI visualizations. And I hope you can borrow from them and create better tools, whether it's at the CLI or whether it's at GUIs. Because I think there's a lot of opportunities. It's exciting to work with traces, and that's a quick tour of some of the things we can do. Thank you.
We've got just a couple minutes for questions. If anybody has them, we'll hand you the mic. Brendan, the audience is stunned. Here we go.
We have a question. Great.
So the question is, what's the difference from BPF project, or the BCC project, and Sysdig?
The question is, what's the difference between BCC/BPF and Sysdig? BCC/BPF it's been a project to provide programmatic tracing into Linux. And some of the new tools I'm developing are using it. Sysdig has a Lua-style interface and an interactive Sysdig tool. And there are points where they've been much more developed. And so there's a nice set of analyses you can do with Sysdig. How I see the difference, BCC, BPF currently are pretty good if you want to hack at a low level and get into different layers of the stack. Like I go into the kernel, into different areas that Sysdig currently doesn't instrument. Sysdig has quite an expressive one-liner syntax. And so I can do OpenSnoop as in fact, let me just show you the difference between them. So I can do OpenSnoop as because I was trying it earlier. So this is Sysdig, and this is BCC BPF side by side. They're pretty much doing the same thing. That's Sysdig. It has a very expressive and powerful syntax, Lua-based. Here's BCC. Can do the same thing. The tool itself is 183 lines long, so it's not one-liner. It's more powerful. I've got more control over what I'm doing. Here I'm doing stuff in the kernel. So if you're a power user, you'd probably like to hack on this stuff. But it's also pretty hard to hack on this stuff. On the other hand, with Sysdig, you have a really nice, concise front-end language and a lot of documented chisels. But really, the main things are it's more powerful when I go into the kernel, but it's also much more difficult to use. Yes?
Hi. You mentioned that testing these tools is one of the bigger difficulties. Do you have any tips from your experience on how to properly test them?
The question is about testing tools, and I think I need to get better at that personally. Back when I did the DTrace toolkit, I had someone do basically a smoke test where they would just run each of the tools and then see if they blew up or not. That proved pretty useful, but that's really step one in testing. I found it really difficult to be able to test tools that monitored system performance and to be able to separate that out from noise on the system until you get far too many false positives because other stuff was happening, cron tabs were kicking off when you're trying to test the tool. How can we fix that? I do a lot of manual testing, and for networking, it's problematic because I often need multiple hosts and I need to be driving workload. I guess my answer is I think it's something that we need to develop that I haven't been really good at, but I hope in the future we can come up with better ways to test these tools so that they don't break, because it's important. I mean, individually at like a language level, there's been lots of tests. So DTrace has a massive test suite, BPF has tests, BCC has tests. So we can test functionality for regressions, but actually testing the output of a, say, network monitoring tool and making sure that the kernel hasn't changed the code path and now we're missing some send receives. That's really tricky because it can happen.
All right, one more round of applause for Brendan, please. Thank you very much, Brendan. All right, it is lunchtime. So lunch is out where the beverages and refreshments were earlier. Also, just so you know, there's plenty of outdoor space, and there are also some chairs in the patio back on this side, so you can get a little sunshine if you'd like. Right after lunch, we'll come back to do troubleshooting Kubernetes with Gianluca, and lunch will be 45 minutes. All right, welcome back for the afternoon session. One more announcement before we get into the next session. As many of you know, this afternoon we're going to do a contest using Sysdig and Falco. It's called the Find the Hacker contest. And in order to participate in the contest, we need you to join our public Slack channel, and that's sysdig.slack.com. And you're gonna use that as part of the contest. So once you join there, you'll be auto joined to a particular Slack channel, which is Falco CCWFS, and Mark will give you instructions on that later on. Okay, cool. Welcome back, and please welcome back to the stage Gianluca Borello for round 2, troubleshooting Kubernetes.
All right, here we meet again. It's about time to give containers some love, right? So this part of the talk will be focused around troubleshooting containers and Kubernetes. It's pretty much all live, and I'm going to present you some real use cases that in some variety happened really on the field with us. And let's get started. I'm just going to spend a couple minutes going through these boring slides before jumping to the action. So this image reflects pretty well what my ideal experience with containers should be like. Look at how well polished and clean data center it is. So ideally, if I'm introducing containers in my infrastructure, it's because I want the entropy of my system to go down, so that then I get advantages such as more cost-effective applications, faster deployment, flexibility, and all that. And that is really the ideal world. I've been working with containers for about 3 years at this point, and what I found out is that most of the time, this is the real experience with container. This is what really happens, in my opinion, with containers, because you find out that containers now put one further layer of isolation between you and your processes. They are scheduled everywhere. They move around. And very important, they talk to each other using these crazy virtual layers of networking stacked one on top of each other. So again, I have had less than ideal experience with containers. And the industry standard response to this need of the community has been essentially to come up with cluster orchestrator. So software components that can abstract away the complexity of maintaining and operating your containers in the infrastructure. So Kubernetes, or Mesos, or Docker Swarm, or whatever you want to put, they take essentially the task of getting your containers as an application developer and scheduling them on your infrastructure using some higher level semantics that you can reason with. So ideally, you don't have to interact with containers that much. And that is always fine until your application works, right? Because when it works, Kubernetes does its job and does its job very well. But at some point, your application will fail, or you will have to troubleshoot it somehow. And it doesn't matter that Kubernetes is handling it for you. You will still have to face yourself with your containers. And so you will have to struggle with the fact that containers are isolated. So you have to face significant challenges when accessing the application inside them. You have minimal runtime. So you don't have all your tool belt of system troubleshooting tools installed in your containers. And they are all moving around. And what I am describing is really not just a marketing pitch or some sort of propaganda because I work for a monitoring company. It's a real need. For example, while I was preparing this presentation, I looked on the GitHub issues for Kubernetes, and I found this one where this guy from the Kubernetes community said, yeah, there is a bug. We have clearly a 20-second timeout on something. But sadly, there are not many debugging tools available in BusyBox, obviously, because your containers is extremely minimal. And then it goes on. If you're willing to dig this further, add this new container and do this sort of random commands. Awful. It has to be much better than that. And so in my use cases, I am going to essentially use Sysdig, not surprisingly. And why Sysdig? Sysdig wants to be wants to be really the troubleshooting and debugging tool that you have to enhance your Kubernetes experience. But you can replace essentially Kubernetes with anything that schedules containers. So this is the use cases I'll show will be focused around Kubernetes, but it's really not Kubernetes specific. What is that needs to be said for essentially the integration between Sysdig and Kubernetes? Because it might seem that, yeah, Sysdig just works with system calls, so obviously it's going to work with Kubernetes. As you have seen, and as Luca showed us in his first presentation, all the Sysdig events, they come from the kernel, and then they enter in the state machine where you are able to filter them by specific containers and all that. With Kubernetes and Sysdig, we have Sysdig connect to the Kubernetes API server and fetch the data, the metadata about how your applications are scheduled. So in Kubernetes, you don't deal with containers. You deal with pods that are theme wrappers around containers. Then pods are usually handled in some sort of deployment, which is like an auto-scaling group for your containers that makes sure that you always have a minimum amount of replicas of your containers up and running across your cluster. So Sysdig fetches all that information and makes it available to you inside Sysdig as Sysdig views or Sysdig filters. And as you will see, when you actually do troubleshooting, that becomes quite useful. And so let's, after this very short introduction, let's start about the troubleshooting use case that I have here. I have a couple. They will take a little bit of time going through it, but I think they are very interesting. So the first one is about Kubernetes services. As I said, Kubernetes takes care of taking your containers and scheduling it for you. But it doesn't only provide that. It provides other building blocks for your application, and one of those is the very powerful service discovery. So Kubernetes allows you to create your containers. Then it allows you to create a service on top of that container, and the service works like this. You link a service with your underlying group of containers, and a service will generate a virtual static IP address that is routable within the Kubernetes cluster. Now, every time within the Kubernetes cluster from another container, you reach out this virtual static IP address, it will be automatically routed towards one of the underlying containers. So even without knowing the actual identity of your services, you're able to access them using this static IP address that Kubernetes provides, some sort of easy to discover load balancer. And not only this, but since remembering IP addresses can get, of course, very complicated, Kubernetes also allows you to give to your services a name. And this name will be a valid DNS entry in your cluster. So whenever you try to resolve this service name as a DNS request, it will be automatically resolved to the IP address of the service so that then you can connect to it and be routed to one of the underlying pods. As you can imagine, there's quite a bit of machinery going on under the hood. And as it was said today in the first talk, it's very, very useful to understand what's going on and just learn to appreciate how things work under the hood, because it will become useful when you are actually doing real troubleshooting. So let's start with this. Again, if you cannot see in the back, let me know. I am going to create these Kubernetes resources. So I have a namespace over here. Again, a namespace is the highest level entity in Kubernetes. So I'm creating a namespace, and inside this namespace, I'm going to create a service that is called backend that will listen on port 80, and then I'm going to link this Kubernetes service to this deployment. Again, a deployment is an auto-scaling group of containers. You can think about it. And in this case, I'm saying this deployment will need to have 3 replicas of the nginx 1.10 container. All right? So I'm deploying this to the cluster, and this is really as easy as doing with kube control, create, and I specify the YAML. And this will create me all the resources. You can see they will create the namespace, the service, the deployment, then creates also Redis. We'll see later what Redis is used for. So now I can use kube control to describe my service, And it will show you that my service named backend has a IP address. This is this one, and this is the static IP address. And it's automatically routed to one of these 3 underlying pods. Now, how do I see this magic in action? I can do this. I can create an interactive pod inside my Kubernetes cluster. And so over here, hold on. All right. So I can create, with this kube control command line, I can create a client that runs the curl Docker image inside my namespace that I just created. So it will drop me in an interactive shell. And look, if I do curl backend, automatically I get a response from one of the underlying nginx containers that Kubernetes scheduled for me. And I didn't have to know the identity because I just used the DNS name. Now, how does all this work? To see how this all works, I'm going to use Sysdig and sniff at the system level all the machinery that's going on. So I am going to go into this other shell, and I am going to run this command line with Sysdig. First of all, I'm going to choose to print the Kubernetes fields in the standard output. Then I'm going to enlarge the I/O buffers because I'm going to need them. Then I'm going to choose to see ASCII character, ASCII output, and don't resolve ports. So this was a little bit of a boilerplate. But now the fun part is I want to look at the network activity of my namespace. So with Sysdig, I can use a filter, which is file descriptor type in IPv4, IPv6, and this is the fun part, kubernetes.namespace.name equal critical app. See how Sysdig is able to understand the semantics of Kubernetes, which is what I needed for this troubleshooting. And then I'm also going to put or process name equals skydns. You'll see in a second while I need it. For the moment, just trust me. And if I run this, now Sysdig will sniff everything that's going on in the system. And so if I repeat my curl backend, I see a bunch of stuff that I can then go and analyze to take a look at what actually happened. And it's quite interesting. I hope you can see in the back. Again, if you can, just raise your hand because it's very important that you are able to see everything. So I see at the beginning curl, which is in this container, on the client pod. See how by putting the PK format, I am able to see the name of the Kubernetes entity. That does, of course, a DNS resolution. So the first thing that it does is contacting this IP address, which is the IP address of my virtual machine, on port 53. And then it sends the DNS request. The DNS request, we can see it in plain text over here, is received by skydns, that is the DNS server that lists on port 53 on my machine. This is the DNS server implemented by Kubernetes. And this is the DNS request. Look at how it is backend, then there's critical app, service, cluster, local. So somehow curl understood that backend was not a fully qualified domain name, and it appended a bunch of crap on top, to make it a fully qualified domain name so that Kubernetes could actually resolve it. Now, the ball is in the skydns court because it needs to resolve this DNS entry to a proper IP address. And how does it do that? In Kubernetes, the source of truth is stored in etcd. etcd is a distributed key value data store that contains all the settings. So we can see that skydns starts doing a connection towards etcd because we can see the port 4001. If I didn't filter just for my namespace, I would have actually seen etcd. But then it sends, we can see it sends a HTTP request because etcd is HTTP based, asking for the key for backend, critical app, service, cluster, local. So this is how skydns essentially tries to resolve the magic DNS name. It translates it to an etcd request, and etcd, of course, knows the detail about my service, and it replies over here with an HTTP response that contains, among other things, this, the IP address of the service, 10.3.0.220. This is the IP address that it's actually routable in my Kubernetes cluster. And so this IP address gets then packaged as a DNS response, makes its way through curl, and curl over here, we can see that it does a connect, always in the other pod, it does a connect on the virtual IP address on port 80, and then it sends to it the HTTP request, which is the one that I sent from my command line, right? Get slash. And let's see how this same HTTP request is somehow intercepted by the nginx process, which is in another container in one of the backend pods. What is interesting over here, if you pay closer attention, is that look at how NGINX accepts the connection. And this is the destination address of the connection, 10.17.0.5. But curl connected to a different IP address, which is the magic IP address, 10.3.0.220. So the same connection has been somehow hijacked into the actual IP address of the pod. And this is where really all the load balancing feature of Kubernetes comes in play. And this is done by IP tables. It's very simple. If you've ever dealt with IP tables, you just go in IP tables and you take a look at the network address translation. And you will see that Kubernetes puts a lot of stuff in it, puts a lot of network address translation rules. And we can see mine that says, hey, whenever you see traffic that goes to this IP address on port 80, make sure that you route it towards this IP tables chain. And this IP tables chain contains 3 rules, 1 per every pod that I have. And you can see how IP tables set a probabilistic rule, and you enter in the first one with 33%. Then if it fails, you enter in the other one with 50% probability. And this is how the essentially stateless load balancing is handled by the kernel. So Kubernetes completely defers these to Kubernetes, to the kernel. And that's why you see from the system call point of view, you see the tuple of the TCP connection being different. And once this happens, pretty much everything else is straightforward. So we see NGINX that does an HTTP response, and then the HTTP response makes its way to curl, which receives it from the network. So we have been able to shed some light on essentially the tricky parts that Kubernetes uses to implement services. So dynamic translation of a DNS request into an etcd request, and load balancing at the kernel level using IP tables. Now, you will probably be thinking, all right, seems that everything works fine, so nothing went particularly wrong. But since I am a very thorough engineer, the first time I implemented this, I followed the Kubernetes guide, and the Kubernetes guide said that every service in Kubernetes gets a DNS name that is under the form of service.namespace.service.cluster.local. So since I wanted to avoid any ambiguity in my code, in the original curl code, I put the fully qualified domain name over there instead of just backend because, right, why not? So that I avoid entropy once again. And this is what happened. So I put critical app, service.cluster.local, shoot. I get curl that hangs in there for 10 seconds, and essentially not only it hangs in there for 10 seconds, but then it correctly sends me the reply. So as a distributed engineer, that's the worst thing. You want things to fail. You don't want things to take 10 seconds and then succeed. That's horrible. So I am going to use now the same sort of troubleshooting that I did in the first use case to figure out what's happening over there, why the fully qualified domain name didn't work. So I'm going to be using the exact same command line, except that this time I'm going to create a Sysdig trace file so that I can then passively analyze the input without having to replicate it any time, which is very powerful. As Adam has said at the beginning, you don't want your troubleshooting tools to harm your processes. And that's the perfect way. Like you're in production, you just sniff it passively, and then you analyze it on your laptop. So if I do sysdig -s, let's enlarge the buffers. If I do this, now Sysdig will going to be saving on the trace file everything that's happening in the system. And I repeat my horrible issue over here. I wait until it succeeds. Again, it takes about 10 seconds. And once it succeeds, now I have a very rich trace file that contains all the activity that went on in the system. And then I can explore it. Again, I'm starting exploring it with the same exact command line that I used before. So I'm just going to go over here and read the trace file. Once I read it, I see a bunch of stuff. And I can start analyzing it from the beginning, trying to spot the differences. We can see that the beginning is pretty similar. Curl does the connect to the DNS server, and SkyDNS receives the DNS request. But something immediately sounds odd. The DNS request is much longer. we have backend critical app service cluster local, and then we have again critical app service cluster local. So it seems like because of maybe some resolve.conf misconfiguration, curl didn't understand that I already passed a fully qualified domain name on the input. And so it tried to patch it in some way by appending the search domain one more time. And this request gets essentially propagated verbatim to etcd over here. So you can see that service cluster local is appended twice in the whole etcd request. And of course, etcd says, no way, I don't know what this thing is. In fact, it returned an HTTP 404, not found. So etcd gives up. I don't know what this service is. You're passing me a bunch of stuff. So then this essentially not found gets its way again over to curl. But curl doesn't give up. And curl tries one more time with a DNS request which is similar. It's backend critical app service cluster local. But this time it just appended service cluster local. So we are missing in the appended domain critical app. So it seems like curl is trying desperately to append different search domains in order to get the right one. But of course, this one fails as well. We can see that it makes its way to etcd. etcd reply with 404 not found. 404 not found is propagated as a DNS response to curl over here. And then curl tries essentially one more time, this time with an even shorter search domain, backend critical app service cluster local dot cluster local. So we just have 2 more tokens appended. And this one fails as well, again, with a 404. So it might seem like to the untrained eye that we found the issue because we said, oh, yeah, there's a bunch of inefficiencies that are going on over here. But it's not true. Look at the timestamp. This last etcd request happens at 49.61, but the initial request happened at 49.60. So overall, this whole inefficiency took less than 10 milliseconds. That's because every component it's living in my local machine. So maybe this will just cause more disruption if I were on a WAN where I had etcd somewhere else. But this is really not my case, because here I'm looking at something big. I'm looking at 10 seconds of timeout. The answer is over here. After this last DNS request, SkyDNS tries one more time, curl tries one more time with this new URL. Backend.criticalapp service cluster local dot local domain. This dot local domain is something that is not being recognized from SkyDNS as being a valid domain name for Kubernetes. And so instead of going to etcd, it decides, oh, I need to forward this dot local domain request to my upstream DNS server, right? And in fact, we can see that SkyDNS then contacts my upstream DNS server, which has another IP address, probably that was discovered via my DHCP setting. And it forwards the DNS request to my upstream DNS. And notice how if you look at the timestamp, then it stays hanging for 4 seconds, between 49 and 53. So we are spending 4 seconds waiting for the reply for the .local domain request, which of course is probably just thrown away from my upstream DNS server because .local domain is not a very mainstream domain name, right? So a DNS server has all the right to ignore it. And so we are spending 4 seconds. And then SkyDNS tries one more time. We can see over here that it tries to send the request one more time. And in fact, we go from .53 to .57. So we spend 4 more seconds. And then we spend 4 more seconds once more. So overall, we spend 12 seconds in trying to resolve a DNS request that wasn't even there, like for a domain name that doesn't exist. And then finally succeeds. Why succeeds? Because as a very last resort, curl decides to, OK, whatever. I'm just going to stop trying to patch things, and I'm just going to pass the domain name verbatim as you passed it from the command line. So you can see backend critical app service cluster local. And this is perfectly resolved by etcd. In fact, etcd returns the IP address. And after that, all the request goes through extremely fine. You can see how the HTTP request goes, gets captured by IP tables once again, and gets handled by the nginx pause and makes its way over there. So by looking at things at the system level, I've been able to see that I clearly have 2 issues. The first one is that curl didn't trust me when I provided a fully qualified domain name in the command line. And the second one is that that dot local domain made its way into my containers, even though it should have never been there because it's not routable within the Kubernetes cluster. Good troubleshooting. If you have been this far and you've already done network troubleshooting before, you will say, why did you use Sysdig? I could have used TCP dump. TCP dump has a nice DNS decoder that shows me the DNS request and response in a user-friendly way. My response to this is, first, good luck in running TCP dump in your container, because most of the time, actually, 100% of the time, you don't have it in your tool belt inside your Docker image. And second, even if you want to run it outside your container, good luck finding the network interface matching the network namespace of the container that Kubernetes scheduled it. But these are weak motives. I understand why some will be skeptical. I mean, TCP dump is a great tool. So the real reason is that I'm not done with the troubleshooting, because now the natural progression of my troubleshooting is, let's take a look at resolve.conf and let's see what was in there. But my container could have been long gone because this was a production issue. But hey, I have a Sysdig trace file. So I can just use the exact same command line and strip away the filter on the network activity. And now we are talking. Now we see a bunch more stuff, including the resolve.conf as it was read by curl over here, because of course the libc linked inside curl read at runtime the resolve.conf. And the resolve.conf shows us exactly the answer to those two issues. The first one, you can see all the search domains that are appended, and you can see how it's stripping one token every time. And then at the end, we have the dot local domain. So these answer why we were seeing those different DNS requests, those 4. And then also the last option, options n-dots 5, will show you why curl didn't trust me when I gave it already a fully qualified domain name. It didn't, because n-dots 5, if you read the man page, means whenever you give a DNS resolution for a host name to the libc with less than 5 dots, I will not treat it as fully qualified domain name, and I will try to first append all the search domains into it. So this was the reason why. There are very good reasons why, of course, Kubernetes put it n-dots 5, the biggest reason being so that I can just type curl backend. But clearly in this case, because of my local domain thing, it screwed things up. And there is one more thing that I can answer, which is why exactly local domain ended up in there? Who screwed up so badly that injected this wrong local domain inside my container? And probably the culprits could be two, right? Could be Docker during the container creation, or it could be Kubernetes when it instructed Docker to create the container. Let's take a look with Sysdig. You will see this thing will pretty much amaze you. So I can take the exact same command line as before, but now I can look. Since I know that all the control plane between Kubernetes and Docker is handled by a Unix socket, I can now filter for Unix sockets. And look at this. Since I'm interested in all the control requests that contain local domain, I can do evt.buffer contains local domain. So now I'm using Sysdig as a grep for your entire system. I'm actually going to use the echo file descriptor Chisel so we see some nice colors. Oops, what did I do? Oops, I missed a space over here. And if I create a new client, now I will see over here, okay, oh, hold on, I think there's some, okay. I put IP Unix, which is wrong, right? Sorry guys, working on this small screen is a pain. Okay, here, local domain, and this will show me all the activity that was actually intercepted during the control plane and just the activity that contained essentially the local domain token. So I can see that Hypercube, which is part of the Kubernetes control plane, wrote on var run docker.sock a post to container create for creating my client container, which contains a bunch of stuff, but most importantly, it contains the local domain token over here. And so we can see that one of the options of the JSON was the DNS search, including all those four search domains. So the culprit in this case was clearly Kubernetes. Really, it's mine because I'm sure I misconfigured my system somehow to handle the local domain. But this should be the final answer as to why I use Sysdig, because I've been able to look at things, not only from the network point of view, but I went to the file, and then I went to the Unix sockets. And this was really across containers. I've been able to see inside the containers from outside the containers. So this was the first troubleshooting use case that I had. I have a shorter one, and this one. So again, this was the thing I was telling you about, the frustrating timeout by the DNS request. The other one that I have in mind is rolling deployment. Kubernetes not only takes care of scheduling your containers and making your containers easy to discover, Kubernetes also takes care of making sure that you can update your application with as minimum disruption as possible. So when you create a deployment and you choose, OK, I want to upgrade the image for my deployment because I shipped a bunch of bug fixes, Kubernetes will make sure to bring up the new containers and making sure that they are healthy before bringing down the older containers. And this is essentially a concept of rolling deployment. It's extremely powerful. And I want to show you what happens when it doesn't work. So over here, I'm using the same infrastructure as before, but I am deploying this other additional component, health checker. Health checker is a little component. It's a Go application that I wrote that essentially periodically checks the status of a Kubernetes service, passed as a command line, in this case backend, and then it reports its status onto Redis. It essentially reports the service response time. So if I deploy these on my machine, health checker, and now I use, for example, Sysdig, just so we see a little bit more things, and then I go to the Kubernetes pods view, I am able to see all my pods, all my containers, and the health checker over here, if I press F, Sysdig is able to dig into the Kubernetes essentially containers and take a look at the log. So you can see that my service is pinging it, and then it's returning 17 bytes, and it tracks the response time. Very efficient response time because everything is local, obviously. And if I want to see how things work, I can use the echo mode, for example, and I can see over here how all the I/O that my thing does. And so I can see that my health checker talks, obviously, to the virtual static IP address of the service. It does the HTTP request, and then it gets the HTTP response, and then it prints on screen the service, the log line, and then it goes into Redis and saves inside the key backend the same response time. So this is very cool. Let me show you also how it looks like if you look at something a little bit more creative. This is Sysdig Cloud. It's just essentially a distributed extension to Sysdig. And here I can observe my namespace in Critical App, and I can see all my containers, how they are sliced by the deployment and by the individual pod and by the individual container. And then I can see my health checker. And notice what cool it is, that if I click on my deployment, and then I look at something such as the topology map, I am able to see in real time how Kubernetes is making the whole thing work. So I can expand my namespace, and look at how the health checker is talking to the backend deployment and to the Redis deployment. And I can expand this, and I can see how the IP tables thing work. The gray box is the essentially virtual entry for the service. And then I can see how, you can see that how IP tables routes every second. You can see how essentially the link changes and highlights a different second every single different backend pod. And this is how the health checker works. And I can expand that, for example, and take a look at the individual container and processes. So this is pretty cool. But what I wanted to show you is this other thing, which is the rolling deployment. As I said, my thing is an extremely critical application. So if I do Sysdig, and I keep taking a look at the Kubernetes logs, and then I do a rolling update, nginx over here. Here, I'm deciding to bump, with kube control, I'm deciding to bump the image of my deployment to one new version of nginx, 1.11. If I do this, Kubernetes will create, under the hood, new containers, and will bring them up, and see how the logs in the lower portion of the screen never report an error, because, of course, because of the rolling deployment. This update doesn't cause any service disruption. And if I don't believe that I have a rolling deployment, I can go, for example, once again, in something like Sysdig Cloud, and I can track a metric like the container count Okay, the resolution is extremely small. I can take a look at a measure like the container count, and I can see that my monitoring system is putting me that there has been some scaling activity from Kubernetes. And then for one instance, the container count went to 4, and then it went back to 3. And this was while Kubernetes was replacing all the containers under the hood. And it's much more clear if I slice the container count for my deployment by a label that Kubernetes puts, which is the template hash, which is the generation ID of my pods that gets updated every time I do a rolling update. And look at how this chart now looks. You can see how the old copies of the containers are being decommissioned, while the new copies of the containers are being essentially commissioned. And these two lines, they meet pretty high in the whole vertical space, which means that there was no downtime. And so, again, you will see why this is particularly interesting, since everything worked fine. Well, it didn't, because in my original implementation, I used something else in Kubernetes, which is essentially a headless service. I lied when I described how Kubernetes services work. Kubernetes services have one implementation, which is the one that works through virtual service IP address, but there is another one, which is called headless service, that works by not providing a single IP address, a virtual IP address, but it works by just exposing in a DNS round-robin fashion the underlying IP addresses of the pods. That's needed when, for example, you have a client connection that needs to be aware of the actual IP addresses of the pods. For example, if you use Cassandra inside Kubernetes. So creating a headless service is as simple as recreating all my service by putting cluster IP none. And when I create it over here, and then I create again my health checker, if I describe my service, you will see that the IP is none, and now I just have the IP addresses of the underlying pods. So now my health checker, if I go and take a look, my health checker is still working fine over here, and is logging. But if I do a rolling update, somehow it will break. Error during health check, and it will not recover anymore. And yet, the rolling update completely happened. I can see over here that I can see the scaling activity. I can see a surge. Actually, we even saw a surge to 6 containers. And I can slice them by the pod template hash. And I can see how the new generation went up, and the old generation went down. So the issue in this case was very easy to find with Sysdig, because I went over here, and I can just look at the I/O activity of my health checker container, and I will find over here that essentially the health checker is still trying to connect to one of the old IP addresses of the pods before my rolling update. So what happened is that in this case, I had a client bug, and my Go client, since I was very sloppy, I cached the IP address instead of resolving it at every health check, because I said, oh, well, the IP address in the Kubernetes service is fixed. So it doesn't matter if I cache it. But by caching it in a headless service, you essentially disrupt everything. And that's how I found it. And it's pretty interesting because, for example, if you take a look at the bypass that this health checker in the headless version will do if I don't have essentially the headless service, I can just kill my health checker, and Kubernetes will spin up, of course, a new one, which will work just fine. And I can go, for example, in my monitoring system and taking a look at the map. And you can see how this time, essentially, the map is fundamentally different. Notice how the health checker container, is directly talking to one of the green boxes. So I don't see the gray box anymore, which was the IP table's virtual IP address. And in fact, this is an extremely sloppy health checker, because the IP address is resolved just once. In fact, you can see how my health checker is just always hitting one of the replicas of my service, and not all of them. And this should essentially give you a lot of things to think about when you're troubleshooting containers. And that was pretty much all I had. We have on our blogs a bunch of other troubleshooting stories on containers and Kubernetes. But other than that, thank you very much for listening.
Thank you, Gianluca. Thank you. If we do have any questions, we've got time for questions. Please raise your hand and we'll bring a mic over.
Hey there, over here.
Oh.
So what you showed is, did you show a Kubernetes cluster that had multiple nodes, or was it all on one machine? I didn't understand how Sysdig is introspecting containers running across a bunch of nodes in a cluster the way you were showing it. So.
Absolutely good question. So for the sake of this demo, I essentially spinned up a Kubernetes cluster that was all on my machine. What happens when you want to do this on a distributed cluster is that if you use Sysdig, Sysdig will always need to talk to the API server, but you need to run Sysdig on the node where you actually want to do the troubleshooting. So in this case, you would have to run Sysdig on the node where the health checker Kubernetes pod was there. If instead you use Sysdig Cloud is already, Sysdig Cloud has essentially been created to solve that problem, and you have this modified version of Sysdig that reports everything from each node into a central location, so that then you can correlate everything in that sort of map. But Sysdig itself, yes, is limited to single node, so you would have at least to at least find the node where your pods were, and then start operating with Sysdig on there. But you will still see all the metadata and all that.
A follow-on to that, are you running Sysdig in a container on the node, or are you running Sysdig at the local level on the node?
The short answer is that it doesn't absolutely matter. Sysdig can run. For sure, Sysdig doesn't run inside your application container. That would be a big sin. Sysdig, and that being said, Sysdig can run locally on your machine if your machine has, a proper runtime, or if you are on CoreOS and such of those things, you can essentially run it in a separate container, and it won't change anything. The set of features is exactly the same because the data is always fetched by the kernel. Of course, that container would have to be a privileged container, but it's the same set of features. There's really no difference.
Right. So if you want to have a self-configuring or a scalable infrastructure, you can do the monitoring along with the infrastructure. So as you deploy new nodes, you deploy containers on them with Sysdig.
Absolutely, absolutely. You could choose to have your own Chisel that reports to Redis something, and you could deploy essentially the Sysdig container as a daemon set in Kubernetes that automatically deploys one copy per each node, and you will be good to go. A question there in front.
Thanks for your talk.
Sure.
As you were saying before, if you're using Sysdig, you have to basically use it on a single node at a time, right? Is there any way that maybe you can take like a bunch of traces and concatenate them together, and then run Sysdig once and still get this kind of top level like view of all of the processes like together, or like?
So at the moment, with the same Sysdig command line, you can specify multiple times the -r flag, so you can read multiple trace files. But it's not the same thing as reading, as merging the file, because if you run a Chisel, you will still get one Chisel output per, essentially per trace file. But that being said, that's really an implementation detail. Someone, either us or in the community, should come up with the same thing that in the network world you have. It's called merge cap, that will just take many Sysdig trace files and create a single one, and that will just work. And of course, then you will be able to act with a single filter, see all your infrastructure. Yeah, definitely. It could be, but we have a bunch of stuff in the initializer block or the thread list, so that's why I put my hand forward. I don't want to promise anything that doesn't work. Question?
Hello. Yeah. So you used Kubernetes as a container orchestration system, but there are like other container orchestration systems as well. Does the demo that you provided, is it like independent of the container orchestration system, or did you kind of like have to deal with the specifics of Kubernetes?
So the short answer is it's absolutely agnostic because wherever you can run containers, Sysdig will just work. If you want the cluster orchestrator filters, at the moment we support Kubernetes and Mesos. Most of the time, though, you will end up finding that your cluster orchestrator, even if it's completely obscure and not mainstream, it's still forwarding some labels inside your containers, so you can still use them inside Sysdig, even if Sysdig doesn't provide official support. Of course, things specific like the service discovery that I showed, those are really Kubernetes specific. Mesos does something completely different from the load balancing, or even Docker Swarm, they use different facilities. But the idea that I wanted to convey is that you can still do it. Like, if you know your system, then you're able to effectively troubleshoot it, even if it's in a container.
Time for one more question, if anybody has one. All right, thank you, Gianluca.
Thank you.
Next up, Loris Degiani comes back to the stage to talk about advanced application debugging.
All right. I'm going to spend the next 30 minutes to talk about tracing, as in transaction tracing, based on tracing as in system call tracing. So my talk is already becoming confusing even before I start. So as I was mentioning in my welcome speech this morning, there are a few things that we pushed out in Sysdig as, let's call them experimental features during the last few months. One of these is a functionality that we call tracers, and essentially makes it possible to inject custom markers inside the Sysdig event stream and do fun stuff together with it. So I want to tell you a bit about how it works, and then give a few demos interactively in my Linux virtual machine. Before we do that, a bit of context on this. So Luca showed these diagrams this morning as well. This is the basic Sysdig capture diagram. We have a kernel, we have a bunch of processes on it, we have processes that can sit inside containers, and it doesn't matter. Sysdig is able to essentially, through the kernel module, to capture the system calls and system events, and then consume them and create a stream. The stream looks, and now you're familiar with it, looks a bit like a sequence of operations that the different processes are doing on top of the kernel. So Sysdig is able to dump them to disk, filter them, let you analyze them, and all of the fun applications that we've seen in the previous demos. Sysdig tracers are a way to actively inject events inside the stream. These events can be used to mark the beginning and the end of what we call spans. So through tracers, you can essentially mark the beginning of something and the end of something. What something means is arbitrary because it's inside your code or your scripts. But examples of what you can convert into spans is function calls, requests, or any arbitrary piece of execution inside your code. Tracers are usable from any language. In particular, the trick that we use to implement them is you write something to /dev/null. while using /dev/null instead of something else. When we started working on that, we first experimented with creating a custom device to collect this information, like in /dev. But then we also wanted this to be container friendly, which is one of the bullets on this slide. So we want containers to be first-class citizens in this kind of functionality. And dev/null is always there. It's available no matter what. Even in the simplest possible container, dev/null is always there. So if you can write to dev/null, you can emit a Sysdig tracer. And if you do it from inside the container, we're still able to capture that write, and we're still being able to inject it inside the stream. The other goal is low overhead instrumentation. So this is not, let's say, as low overhead to go to like something like a profiler. That's not the primary goal of this, but it's low overhead enough that if you are tracing a distributed application, especially a containerized application, this should be completely negligible. So we had as a goal being below 1 microsecond in overhead to emit and collect these tracers. So in practice, going back to the list of system calls that I was showing before, it's possible to essentially write to dev/null and start having these red events that are interjected with the rest of the Sysdig stream events. And then you can just consume them the usual ways you do with Sysdig. So you can print them on screen, you can create chisels on top of them, you can do a bunch of stuff. Events always come in pairs. So you always have an enter event and an exit event. And the combination of an enter event and an exit event with the same ID and the same name is a span. Spans you can have multiple spans inside one or multiple applications running on the same machine or multiple machines. And it's possible to create a hierarchy. So you can have parent spans that contain child spans. So in practice, this allows you to implement something similar to stacks, right? Because you can arbitrarily go essentially deep inside your code or inside your application and create a stack out of that. The format is, we have a couple of formats, but essentially you do text writes to dev/null, and then the Sysdig capture driver is able to interpret these and convert them into the proper events. And there's a simple format that is just a text string with columns as separators, and you have essentially the direction, ID, arbitrary number of tags, and tags also define the hierarchy, and then arguments. So for example, if you're creating a span of a system call, you can have the enter or the input or output arguments of that function call converted into span arguments. Or there's a JSON format that is a bit less efficient, but it's a bit more versatile, especially in the kind of strings that you can use. The simplest possible example is tracing of shell scripts. So I know it sounds sort of crazy as an idea, but this is pretty much an example of APM for a bash script. And what this does is pretty self-explanatory, but this is essentially a pinger script that goes and curls the Sysdig website in a loop. And essentially what we do is we start a span just before the curl, and we close that span when the curl is done. So essentially we are measuring in a loop how long does it take to download the sysdig.org web page. Before I go into examples, a sort of somewhat limited list of fun things you can do with tracers. Measure latencies in your code. In particular, as a developer, many times you want sophisticated ways to get stack traces or latencies, and there are many powerful tools to do that. But very often, I just want to throw a quick measurement in my code. So how long does it take on average to run these requests or stuff like that? And tracers want to be a really user-friendly way to do that. And then, as I will show you in the rest of my presentation, we offer a bunch of tools that allow you to filter, visualize, or display this information. You can save them to trace files, exactly the same way you do it with Sysdig, and they go in trace files with the system events. So you can analyze them with both the text-based Sysdig and Sysdig. You can inspect system activity inside the execution spans. I will show it later, but the system events are intermixed with these. So you can create filters, and you can see what happens just inside one portion of your code. And do a bunch of other stuff like log monitoring that is trace-based, or latencies, test the output, and a bunch of stuff like that. All right, so that's the context. Let's go into my virtual machine. Is this readable? Should it be a bit bigger? Yes, no, yes, OK. Actually, this is the same script that I was showing before. Actually, I have two versions that are currently running on my machine. One is pointing to Sysdig, the other one is pointing to Google. OK, so I can go back to my shell and do something like just applying a filter for the tracers, and I can essentially use Sysdig to filter and look at those tracers. Of course, I can use the Sysdig filtering syntax to do something like and span dot tags equal Sysdig, and I can essentially use exactly the same filtering languages to manipulate tracers, and in this case, I'm excluding the Google ones, and I'm only showing the Sysdig ones. I can also do something like customizing the output, and in this case, instead of just showing the standard command line, the standard line output for Sysdig, I'm printing the duration of the span as a human-readable string, and the filter is still on the Sysdig. So I'm looking at the ballpark of how long it takes to ping, to curl the Sysdig website. As you can see, sometimes it takes very long, 5 seconds now. So that is a quite good indication that the network here is pretty crappy. Another way to observe the same thing is using Sysdig. And in particular, what I'm going to do is I'm clicking on F2 to go to the views, and then I'm going to the bottom. There's a view that is called traces spectrogram. So we've discussed the spectrogram representation multiple times today. It's one of the ones that Brendan showed during his presentation. By the way, look at the network here. So let's pause it for a second, because this is interesting, actually. I can see in the spectrogram. So what I'm doing is now this spectrogram is limited to just the tracer. So I have spans. I have two things running, right? Google and Sysdig, and they are doing requests. Every time one finishes, we are mapping it in the spectrogram. The spectrogram has time on the x-axis. So, and then the color is how many hits I get in the time interval. And every line that scrolls down is a different half a second, right? So we are essentially seeing the progression of the spans, and we clearly see two different vertical bands. Okay. And then we see once in a while a clusterfuck. You see there's something that is in the 10 milliseconds and something that is in the 100 milliseconds, and then everything goes to hell once in a while. I was already observing this morning, and so I actually took a trace file. So this shows that you can save. You just do a Sysdig -w, and you write everything to disk, and then you can just reopen the file and apply the analysis. So this is just a trace that I took this morning on this network. So let's go back down to the traces spectrogram. And this shows the behavior, essentially. So a 10 to 50 milliseconds band, an 100 plus millisecond band, and then once in a while a clusterfuck area. So One functionality that I introduced in Sysdig spectrogram is the drill down capability. So I can use my mouse. This is a terminal, by the way. So it's quite brain damage to work with the ncurses library to implement mouse, and it still doesn't work well on Mac. It gives me headaches, but it's pretty fun. So I can zoom in an area and click on it, and I see essentially the spans that are in that area. So the first area is Google, as you can see. I can go back and pick a bit of the slow area. The slow area is Sysdig, so Google wins, essentially. I don't know how Google can be better at delivering their website than Sysdig, but they are. Now, if we go in the clusterfuck area, it's a bit of Google and a bit of Sysdig. So that's a clear indication that once in a while, every, I don't know, like 20, 30 seconds, the network here goes a bit nuts, and everything becomes slow, you know? So even Google, that was much faster before, now it's as slow as Sysdig. So that's a good, you know, interesting use case of very trivial. Again, let's go back to the script. It's just a matter of echoing something, you know? So even as I was saying before, you know, yeah, there's sophisticated stuff that you can do as a developer, but very often you just want to measure basic stuff. And a trivial method like this with a bit of visualization on top can help you. And visually things, you know, pop up much better. Of course, you also have the option of being more sophisticated. So one thing that you can do is -c tracers to Sysdig. So this is a Chisel that just a Lua script that takes filters on tracer information, extract the spans, and then just sends all of the information out as Sysdig. So for example, I'm running it now. I also have the Sysdig Cloud Agent running on the same machine. So this thing is piping Sysdig to localhost, and the Sysdig Cloud Agent picks it up. And then I can go in my Sysdig Cloud user interface, and I can see that I have a Google and the Sysdig. And here, you know, essentially I can see my thing collected in a centralized place, and I can, for example, easily create an alert on top of these if I want. So we go from instrumenting a shell script with just a write to dev null to being able to pipe it to a centralized monitoring system with, you know, just essentially a single command line. All right. So this is essentially the basic functionality. Now, what I'm going to do is I'm going to run a script, a Python script. Actually, let me show you the script first. This is a bit big. OK. Now it's a bit small. We have a bunch of community created libraries to essentially leverage this functionality from inside your scripting languages without having to actually physically write to dev null. I'm using a Python one here, and I'm essentially decorating a Python script. As you can see, I import the tracer library, and then what I do is I can use the with syntax in Python to decorate a piece of code as I want to trace it. So everything inside this with will be traced as read. And I'm creating a Python script because I want to show the hierarchical capabilities of this. So as you can see, I have 3 high-level spans here. One is read, the other one is process, and the third one is write. And process actually has 2 subspans. So this shows essentially how this can work in a hierarchical way. Let's start the script. And if I go back, actually, let me go to Sysdig. And this time, I'm picking a view that is called traces summary. So this gives me an overview of the traces that are being generated in this system, and gives me the average time, the minimum time, and the maximum time for these traces. I can also see the number of childs, so I can see that process as childs. And I can just select it, click enter, and now I'm inside it. And so it's a bit like hierarchical navigating a stack. As you can see, with language support, this comes pretty natural and allows you to essentially do a drill down exploration of something that could be a bottleneck in your application or inside your code. So that's, basic concept of hierarchy, and I can see it event.type equal tracer. I can see how it works. Essentially, Python is generating, let me actually do and proc.name equal Python. So I filter out the curse. And I can see how Python creates, some spans that are basic spans and some spans that have a hierarchy, and then Sysdig is able to pick that up. Now, there are a couple of things that are interesting that we can do at this point. The first one that I want to show you is, of course, you can do something like span.tags equal write, and at this point we only get the tracers that correspond to the span. But there's also another syntax which is eventin.span.tags. And now what we do is we have Sysdig that is filtering and it is emitting only the system calls that are within the spans that respect the filter that I provided. So this is sort of we know that Sysdig, by default tends to be pretty verbose, and this essentially allows you to limit the output and what you get from Sysdig to specific portions of your code. So it's like putting, again, application tracing together with system call tracing. And the concept is pretty basic, but it's pretty powerful. So I want to show you a couple of things that you can do with it. The one that you can do is apply chisels to the specific filters that you have. So if you look at my simple Python script, I actually have a log function that writes data to app.log, and then I have logs in different points of my application. So I can actually do something like Sysdig and apply a chisel like spy logs. And spy logs essentially looks at every log that is written in the system, both to syslog or to files that end in .log or f.log in their name. So as you can see, it's pretty verbose. At the same time, I can apply this chisel to events that are in a specific span. So now I'm looking at the logs that are generated in a specific span of my code. So logging in the context of something that you have defined that is happening inside your application, either if it's a local application or a distributed application. I'm very fascinated by this concept. I think it's much more powerful than just this demo. So what I did was I put together a visualization for this. I worked together with one of Sysdig's front-end engineers to try to find an interesting and creative way to put everything together in something that is nice to see. And I actually implemented also a relatively more complex microservice-based demo in which this is the Sysdig cloud map of the demo, essentially. So I have a movie theater application with users and movies, and then there's a tier in which there's a user manager, a movie manager, and the cache, and then the movie manager goes to a queue, and everything goes to the database, okay? Let me see how this shows. This is the flame graph representation of the same infrastructure. So this is multi-container. I did the work of essentially passing the tags and the IDs across multiple containers. So that requires a bit of work because you need to be able to, either in an HTTP header or something, pass your tags to the next tier if it's multi-container. And then I collect everything. This is essentially the multi-container flame graph of our movie theater application. So Brendan is sitting here with us. This is, one of his signature contribution to the world of tracing and performance management. I'm sure that all of you are aware of how a flame graph works. They are a powerful tool that many of us use. But to summarize, essentially we're seeing, well, first of all, here we're seeing two different entry point transactions in this little microservice application. One is called users, and the other one is called movies. And we have 10 calls for each of them. I'm selecting the average one, so I'm selecting users. So this is the whole time that user takes. And these are the different components, so the different successive calls. And the color here identifies a container. So by looking at the color, I see how the tree of calls goes from container to container. Okay, so I can look at the average time, but I can also take the slow transaction, the fastest transaction, or the slowest transaction, and I can see how they compare. Now, this is the users. If we look at the movies, we see that the average is 700 milliseconds. The minimum time is 400 milliseconds, and then the maximum time is very slow. It's 2.5 milliseconds. So I can click on the slow one. And one thing that I've implemented in this flame graph is you can click on any of the spans in the visualization, and at the bottom you can see the logs that have been emitted on the span. So I can essentially explore transactions, and I can click around, and I can see what are the logs in the different pieces. So it's like flame graph and transaction monitoring plus the logging. And it's interesting because, well, by the way, I have two options. One is this span only, and the other one I can also look at the childs to essentially get a view that includes the childs of this span as well. But let's go back again to our movies and to our slow one. If we look at the logs, we can see that the movie queue span has an error which says database connection lost. And after that, you can see reconnecting to DB and connecting to DB, which takes essentially 2 seconds, which is also most of the time of this transaction, which also corresponds to the maximum time that we're seeing here. So the slow transaction here seems that like it's being caused by the movie queue container losing the connection to the DB and then reestablishing the connection, which we can see pretty well here. So, by the way, this is not, this is more like a weekend project, this visualization, but if somebody finds it interesting, I will be happy to clean it up and push it on GitHub together with the other chisels. But it's just a chisel that collects this information and then packages everything in a web page with a bit of the tree code. This is essentially how much time I had for this. You find more information online. We have a pretty decent manual on the Sysdig wiki, and we have integration for Python, Node, and Go that you can go grab on GitHub as well and start experimenting with this. I promise you, it's pretty fun. Thank you.
As always, we have time for a few questions if we have any from the audience.
So for the filter you did for the event in span.tags, what kind of logic is it using to determine what is eligible to be within the span? Is it just time-based? Is it more?
Yeah, that's the most complicated part of the code, essentially. And it looks at, first of all, at the tracer enter and exit tracer properties, so ID and tag. It also looks at by default at the thread that is emitting that specific span, but you can customize it. If you look at my script here, as you can see, the ID that I gave is PP, which means parent process, which works well for scripts because it's essentially that tells that you want to get all of the events that are in this process and in the parent in the processes that have the same parent process. So you have, depending on what you write here, you can put a number here as the ID, and at that point you have your unique transaction ID, or you can use a couple of these acronyms. One is T and is for thread, the other one is P and is for process, the other one is PP and is for parent process. And this influence is essentially for this specific span, which events will fall in the event-in filters.
Any last questions? All right, thank you, Loris.
Thank you.
And now please welcome to the stage our next guest speaker from CoreOS, Matthew Garrett, Principal Security Software Engineer. Welcome, Matthew.
Yeah, it says it's... It thinks it's connected.
We have his slides as backup, right? All right, folks, sit tight for just 1 minute while we get it figured out.
Just try this from here.
So we were going to have a break after Matthew's presentation, but since we're having a few technical difficulties, we'll just take the break now. We'll come back in about 15 minutes and we'll have it all sorted. Thanks, everybody. All right, take two. Can I have everybody take their seats, please? And welcome back to the stage, Matthew Garrett.
Hi, sorry about the delay. So my name is Matthew Garrett. I'm at CoreOS. For anyone who's not familiar with CoreOS, we produce a suite of software ranging from the operating system up with the intent of making it easier to build and deploy container-based systems, because fundamentally we believe that container-based solutions make it easier to build secure systems. And I'm going to be talking about certain aspects of that today. But so I'm not actually going to be talking that much about, well, at all, about things directly related to Sysdig, but more about how the container ecosystem as a whole is something that's advantageous both for developers but also for admins. How many of you have had to deal with software security at some point during your professional career? Okay, some of you. And how easy have you found it to convince management that security is important? Yeah, not many of you seem to have really had a good sell there. How many of you have had pushback from other developers or from operations people when you've attempted to implement any sort of security? Yeah, a few. And the unfortunate thing here is that convenience often beats security, which is kind of understandable. If the service you're running isn't working, then it doesn't really matter whether it's secure or not. You're not running a service. And if your entire business model involves you running a service, there's something of a conflict there. So in reality, convenience is, in many ways, the favored party. There's definitely some rigging going on in this scenario. So when we're thinking about security, when we're designing things that are intended to be more secure, we need to design them with the mindset of how can we ensure that users will choose security? How can we avoid them choosing convenience instead? And in this case, basically, making the secure solution the better solution is the only thing that we've really found industry-wide that seems to work in this respect. If we're not able to make the secure solution fundamentally better, there's no incentive for someone to choose the secure solution. Now, this crowd's reasonably young for the most part. How many of you have actually used Telnet for its intended purpose? That's more of you than I expected. Now, one of the problems with Telnet, if you were ever a sysadmin, was that Telnet was not easily scriptable. When you telnetted somewhere, you needed to log in. You couldn't pass a command to Telnet and tell it, run this command on this other system. If you were doing any sort of interactivity, you had to basically script your use of Telnet, which was an unpleasant experience. And then there was that whole having to type a password thing, which meant that you couldn't meaningfully automate Telnet. So people came up with an alternative. How many of you ever used RSH? I'm so sorry. So for those of you who didn't, RSH was this wonderful thing where you typed RSH and then a system name and then hit enter. And it would ask you for your password, and you could type in your password, and then it would give you a shell. But the nice thing about this was you could also type RSH system name command, and it would execute that command on the remote system and then return, which meant that you could write nice scripting solutions. But the problem there was, well, you still need to have the password entered. So you could pass the password on the command line, but then you have your passwords hard-coded in a bunch of scripts, and if you ever change your passwords, that's all terrible. So there was something called the rhosts file. You could create a file in your home directory called .rhosts, and then you could put a host name in there, and then that host name was able to RSH in without a password, which was brilliant in a number of different and terrifying and upsetting ways. This was absolutely a case of convenience winning over security. People used rhosts because it was the easiest way for them to script deploying stuff or updating stuff or making any sort of configuration changes. You write a script that RSH'd into a bunch of systems and then reconfigure them. And then in the mid to late 90s, along came SSH. And SSH did everything that RSH did. This also encrypted it. And it also supported key-based authentication. So you could have the private key on one system and then public keys on a bunch of other systems. And then someone was no longer able to gain access to all your systems merely by spoofing DNS. So SSH was equivalent in functionality to RSH in a number of ways, but more secure, which was wonderful. But it also brought other benefits, like the fact that X forwarding worked magically without you having to type a bunch of extra commands. And people moved to SSH not just because it was more secure, but because it was fundamentally better than both Telnet and RSH. By building a tool that made it easier for people to do their jobs, it was easier for admins to justify migrating to SSH. And we got all these security benefits as a side effect. The only other way we can really increase adoption of security practices is by increasing social pressure while reducing the friction associated with something. The problem with SSL certificates in the past was that, well, firstly, in a lot of cases, the admins didn't gain any security benefit from them at all. It was the users who benefited in some way. And if your security work isn't benefiting you, it's again much harder to justify. But also, renewing your security, your SSL certificates frequently was a gigantic pain. So the easy thing to do was to just run something without any SSL. And then Let's Encrypt came along and made it possible to just script all your certificate renewals, and you could set it up once and then forget about it, and it cost you nothing. And since Let's Encrypt became publicly available, a significant percentage of the internet has suddenly become available over HTTPS that was previously only accessible over unencrypted channels. So those are some examples of where by either making it so much easier than it was in the past, accompanied by social pressure, or by building something that was both secure and also better, security became an easy sell within the industry. But many other examples have been failures. SE-Linux is a security module in Linux that allows you to build complex, basically arbitrarily complex policies that allow very fine-grained control over what individual applications on your system can do, which files they can have access to, how they can communicate with other applications. And adoption is not particularly widespread. SecComp, which allows you to reduce the set of system calls that an application can make in order to increase security, is by and large in the general purpose computing world unused. A small number of applications set up their own SecComp sandboxing, but the vast majority of applications are able to run completely unconfined. Trusted computing is a family of technologies, that make it possible to create an verifiable, auditable, cryptographic log of exactly which software your system booted and exactly which software it then ran after booting. It makes it possible to ensure that your system cannot gain access to resources unless those resources are able to verify that your system hasn't been tampered with, which in a production environment is immensely powerful. But the complexity around it, the amount of work that has to be done to enable this sort of functionality is so far so incredibly site-specific, so user-specific, that its use has been fairly negligible. But moving on, because we're going to be talking about containers, I'm assuming that people here are enthusiastic about containers. You love containers. Good. People want containers for a variety of reasons. And one of those reasons is that containers are just easier to deploy. There's no more, well, I need to install these package versions. And ideally, they need to be these specific package versions because we've been bitten in the past by things being broken in minor revisions. So we need to maintain our own mirror of various packages. And we also can't rely on third-party mirrors because those might go down. Containers avoid all of that because you just stuff everything you need into the container. There's the ease of development. I don't need to worry about validating my code against every version, every possible configuration, every version of everything, because again, I can put the tested, verified environment inside the container, or I can indicate that the container is built on top of this base and then make use of it that way. So the mere fact that we are using containers allows us to think differently about security in a fundamental way. So when I'm talking about trustworthy containers, what I'm talking about is the idea that a container can be something that you can download, something you can verify, and something you can deploy, and you can trust the security properties of that container. You can have those be well defined. And this is particularly appealing in the sense that when we have multiple different components that we're deploying inside containers, we can define what the interfaces between those containers look like. We can restrict those. We can design those in a meaningful way. And this is, again, incredibly helpful because up until now, when you're running a system with a lot of interconnected parts, a lot of the communication between those can happen in a bewildering number of ways. You've got applications that communicate with each other through IP, which is nice and straightforward. You've got applications that communicate with each other over local sockets. You've got applications that communicate with each other over FIFOs. You've got applications that communicate with each other through shared memory. You've got applications that communicate with each other by dropping files into a directory that another application then polls repeatedly. You've got all these ways for applications to interact with each other, and you don't know in advance exactly what those are. So when we're building a container, we can define the interfaces that we are expecting to be present. We build containers usually with the expectation that they'll communicate over IP, which is then a nice, straightforward boundary. It's something that we can control in a meaningful way. We know that if we install a container, it's not then suddenly going to start trying to communicate with other applications in some unexpected way, because it's not going to be able to. We're not sharing those resources. It just won't work. But also, containers let us treat different code differently. We've got a significant set of different kinds of constraints that we can put around containers. We can grant containers only the resources they need. We can grant containers only the capabilities that they need. When we do that, we can end up with containers running in a minimal environment where their ability to attack the rest of the system is again reduced. When you're trying to do this at a whole system level, it's much more complicated. You need to come up with a way of, well, when I start this application, it should be run with these privileges. And the application as shipped is probably not going to provide you with all that metadata, whereas there's much more of a tendency to encourage us to build containers which do only adopt the privileges that they require. And so a kind of outcome of this is that a lot of things that would normally be whole system level issues are not, well, the policy is embodied in the container or the container metadata, but the application of that is moved to the runtime rather than it being something where you need to attempt to apply policy to individual applications. So this is an example of this. How many of you have ever tried to deploy an application, an in-house application, on a system running SE Linux? How many of you have enjoyed that? And this is not a complaint about SE Linux per se. The functionality is vitally important, but it's very complicated, and that makes life more difficult. A typical SE Linux flow involves you writing some software, and then you ship the software, and then a user tells you, well, I attempted to install this on RHEL, and it doesn't work, and I get a bunch of SE Linux errors. And so you're reasonable people. You want to ensure that security is maintained. You don't want to just tell people to turn off SE Linux because that would be a terrible thing. So you write some SE Linux policy, and then you discover that that works on RHEL 7.2 but not 7.3, so then you write some more policy, and then you eventually get that working, and the user says, excellent, this all works perfectly now, thank you. And then you have to keep maintaining that policy in step with RHEL. But that's not too much overhead. And then you discover that people trying to run SE Linux on SUSE have a completely different policy that doesn't work with your policy, and at that point, you add this to the top of your deployment documentation. So our ability to actually trust the software that we're handing to other people, or as admins, the ability to trust the software that we are being given is reduced, because in order to make this software work, we're having to compromise the security of the entire system. We're not even talking about a scenario in which this application is overly privileged. We're instead talking about an application that forces us to reduce the security of the entire system. Containers, this is much easier. You write your software. You put your software in a container, and then you ship the container. And then you don't get any complaints, because in this case, in the container world, the container runtime does the rest. And this is made much easier because, as I mentioned earlier, containers have much better defined semantics for communicating with other containers. By and large, they can't. So we don't need to worry about complicated policy. All we care about is writing an SE Linux policy that says this container should not be able to touch the rest of the system, other than through well-defined mechanisms such as IP, or file systems that I have explicitly shared between multiple containers. And outside that, we can write a very simple policy that just says, no, you can't do that. But another thing that makes people very and somewhat legitimately concerned about containers is the idea that containers have a number of bundled libraries. And like software itself, libraries are made of code. And in many cases, that code is C, and we're really bad at writing C. To be fair, C makes it very easy to be bad at writing C, but even taking that into account, the truth is that libraries often contain security vulnerabilities. And so people will quite legitimately ask, well, OK, you're downloading containers from multiple different third parties. How can we trust that this container does not have a vulnerable version of OpenSSL in it? And to be honest, static analysis of containers is a pretty good answer here. At this point, multiple vendors provide mechanisms for verifying whether your containers contain known security vulnerabilities. Quay now has Claire integrated into it, which will give you a nice list of all the known vulnerabilities in your software. Docker have similar functionality available in the Docker Hub, and then I believe that Black Duck also have something similar. Red Hat have something similar. So these are fairly straightforward mechanisms for you to look at, and then look at your containers and then say, OK, these containers need to be updated. I will update them, and then I will roll the updated containers out. That's pretty straightforward. That's not a disaster. You need to update more things than you did previously, but it's still pretty much an automatable process. And in some ways, this may actually be easier than the traditional solution of we update OpenSSL on every system. How many of you were bitten by the OpenSSL, I think it was 102G update, which was marked as a security update, but which also changed the ABI subtly, such that a small number of applications stopped working? Anyone here hit by that? Yeah, OK, a couple of people were hit by that. Not all OpenSSL use is equally critical. There are many applications that are using OpenSSL for things like its hashing implementations or for RSA crypto, not for anything network-facing. And they're using it for local validation, local signature validation, local encryption. And in those cases, the fact that there's a vulnerability may not be, if the vulnerability is purely in its use in network-facing environments, that vulnerability is unimportant to that specific piece of code. But right now, you don't get to mix and match at the system level. Using containers, you can upgrade the containers that are network-facing as a priority. And then you can, at your leisure, verify whether the upgrade breaks any of the other containers, the containers that are using OpenSSL for much less security-critical purposes. We no longer have to have an all or nothing approach to security, which means, paradoxically, even though we have more copies of OpenSSL, we have much finer-grained control over what gets upgraded. We can build a reasonable idea of how much trust we can place in a container that has a vulnerable version of OpenSSL, whether that is still in context trustworthy. And that way, we don't have to have scenarios where you can't apply a security-critical update until you've verified that 30 different pieces of mission-critical software running on the same systems are all OK with this upgrade. You can do each container one by one, and the moment you've verified that container, you can push out an updated version of that container. So in comparison to the status quo, containers have a lot of benefits. Not only do they allow us to have stronger imposition of security from the outside, we can also potentially end up with more aggressive updates of security-critical components. And even ignoring that, containers are, in many cases, better than the status quo of running multiple applications on the same system. Where right now, if someone compromises your web server, and if that's running on the same system as your database, it's much easier for them to compromise the database as well. Containerizing things means that there is a much stronger security boundary between your different components. Can we do more than this? One of the problems with security is that no security feature provides meaningful security if the layers below it are not themselves secure. Our ability to deploy trustworthy containers, containers that we can place trust in, is dependent upon the container runtime being secure. And the security of the container runtime is dependent upon the security of the operating system as a whole. Now, going back to what I was saying earlier, doing things in general purpose operating systems is difficult. There are so many different ways that applications can communicate with each other. There are so many different ways a system can be configured. If you want to write a general purpose security policy for a general purpose operating system, you pretty much have to provide a very liberal policy to allow people to use that system in ways you have not considered, ways you were not thinking about when you designed it. If you don't have defined use cases, it's very difficult to build a completely secure platform, which means it's still difficult to place trust in the rest of your components. So even if we are talking about the security benefits of containers as a whole, it's very difficult to realize that additional security while doing so with a general purpose operating system. So I have a somewhat heretical viewpoint here and say that maybe in a container world, we shouldn't be building general purpose operating systems. We should instead be building operating systems that are custom designed to allow us to deploy containers in a more secure way, a more trustworthy way. And one aspect of this is that the operating system itself should not need to change. There should be no need to install applications in the operating system itself, because we're putting everything in containers. And in that environment, we don't need any writable file systems that can contain executables. We can have, instead, a cryptographically verified file system that backs our executables. If anybody tries to tamper with the system in any way, the cryptographic verification will fail, and the system will fail, and the attacker will not get anywhere. At best, they've got a denial of service. Google solved this problem with Chrome OS. They implemented something called DM-Verity, which is a layer that sits between the disk and the file system and has a set of chained hashes for each block on the block device. So if someone tries to tamper with the block device directly, the hashes no longer validate, and you get an I/O error when you attempt to read from disk. So there's no way for them to alter the state of the system. When I said trusted computing was difficult because there were so many different environments in which you needed custom configuration, where it was very difficult to build a meaningful policy around trusted computing without being an expert in the field. Having an immutable operating system, again, solves this problem because you now have a strong idea of what the operating system state should look like during boot. You know what you expected the system to boot. You know what configuration you expected to have as it was booting. So these let us build an environment that is a trustworthy base, something that then gives us this environment in which we can then run containers and then trust that the containers will be adequately secured by the underlying operating system. And can we go further than that? So obviously, signed container images are vital here. People should not be deploying containers without a mechanism for verifying that the container images have not been tampered with. But signing is not magical. Signing says this container was at some point signed by someone I trust. A signature tells you whether someone trusted that container at the point in time where it was signed. A signature does not tell you whether a container is inherently trustworthy. So an example of this, if you have a container that you discover contains insecure software and you upgrade the software in that container, how many of you would roll your signing keys for the new container? Nobody. If someone's able to gain access to your control plane in any way, if someone's able to somehow cause your system to spin up an arbitrary container, what stops them from handing over the old insecure version of the container, which still has a valid signature? And the answer is nothing. And at that point, they're then able to potentially exploit that vulnerability and gain access to a system. Signing does not tell you whether something is fundamentally trustworthy. So we can extend the idea of trusted computing. In trusted computing, you have a small piece of hardware called the TPM, or Trusted Platform Module. And the TPM contains a set of registers, and those registers contain the hashes of each component of the boot chain. The CPU verifies the first block of the firmware and puts that into the TPM. The firmware verifies the rest of the firmware. The firmware then hashes the bootloader hashes the kernel, and so on. So you get to an arbitrarily high level of the boot chain, and you know then what the system booted. There's no way that anybody should be able to construct a modified piece of software that will hash to the same value. So we can measure container images as well and push those into the TPM. And then we have a log not just of whether correctly signed images were booted. We have a cryptographically verifiable log of exactly which container images were booted on a system. And we can look at that log, and we can compare those hashes to the versions of containers. And even if someone does break into the system, even if they're able to break out of a container and obtain root on that system, they're not able to do anything to this log other than delete it. If they attempt to change the values in it, those values will no longer match the values stored in the TPM, and so you can detect that the log's been tampered with. So that gives you a completely verifiable audit trail. This allows you to say, this cluster only booted container images that I trust now. Not that it only booted container images that I trusted at some point in history. And we can go even further than that. The reality is that some containers are unequal to others. And that might be because they're running software that we trust less. Or it might be that they contain more sensitive data and we want them more strongly protected. Or it might be that most of our code is deployed in containers and doesn't have to face the public internet, but there's a small number of components that do need to face the public internet. And the question then is, well, are there additional security measures we can apply to these containers? And the answer is that yes, we can in fact isolate some containers more than we isolate others. And Intel developed a technology which a series of technologies that they describe as clear containers. And in a clear container deployment, a container is launched inside a lightweight virtual machine rather than inside a namespace isolated container environment. That way, even if that container is compromised, you're no longer confined by the kernel only. You're confined by the hypervisor, by additional features in the CPU that make it more difficult for you to break out of that container. And you can deploy and manage these identically. From an admin perspective, the only difference between a clear container and a namespace container is, well, the VM-based solution takes slightly more resources, and also you can't bind sockets from the host into the guest. And in principle, there's actually nothing really stopping you from writing a VirtIO interface that allowed sockets to be passed through. But thankfully, I don't think anyone's doing, I really hope no one's doing that yet. But you get the security benefits that we would associate with full virtual machines, which is nice. So even in cases where we don't necessarily trust the contents of a container image as much as we might trust other containers, we can still bring the level of overall trust in the security of the solution up to a level that we're comfortable with by running it in this more isolated environment. If it does become compromised, there are, in fact, even forthcoming technologies that may allow us to automatically detect that a VM-based container has been compromised. So we can build secure container infrastructure. We can come up with things that allow us to build a more secure, a more trustworthy basis for our containers. And we can then build secure, trustworthy containers to run on top of that platform. And, sorry. This means that we can have a much higher degree of trust in the security of our deployments than we would have had with more traditional deployment scenarios. So with that, thank you all for paying attention. And I think we've got a few minutes for questions. Front there. Oh,
sorry, I'm coming.
Microphone.
I understand you said we can trust that the container
does what it's supposed to do in a secure way. What about securing the access to the container? What?
So securing access to the container in the sense of the network access?
Well, let's say if I have a container that accesses the database, what if the access to that container is compromised and affects the database?
Right. So right now, we don't have particularly strong mechanisms in the general sense to have a level of fine-grained control that was allow you to tell the difference between a container that is, under normal circumstances, authorized to access a service and a container that can still access that service if it's compromised. As I said, there's some stuff that we're working on that will allow us to detect that in some of the VM-based containers. In the more general case, if you're willing to accept some degree of performance overhead, it is conceivably possible that we could gain some of the same benefits in a namespace-based environment, but I don't think we have a good general solution for that yet. Something back there?
Two questions. The first one is, what's the difference between running a VM with an app with, say, just enough OS versus running a container inside a VM, which was the last scenario you talked about? And the second one is there ways to restrict which container, can container of this type talk to another container of this type, but only on certain ports, only with certain protocols, being able to restrict how they talk to each other, because in a multi-layered application, you might want to have that.
Right, so to your first, the idea between just running a VM with a minimal operating system and a single application in it, they're basically identical. The question is really more about your tooling. If you're using a container-based environment in general, then using VM-based containers means you don't need to add any additional tooling to that. If you're right now primarily VM-based, if you have no interest in having a heterogeneous mixture of VM-based containers and namespace-based containers, then there's no particular advantage to using the containerized version of it. But if you're in an environment where you are using a lot of namespace-based containers and you have if you would occasionally benefit from having a VM-based container there, then the fact that you don't, it's just, so Rocket implements this, you just pass a different flag to Rocket, and everything else looks identical to how you would bring up the containers in a normal case. As to your second question about more sort of fine-grained control of which containers can talk to which other containers, I'm not really much of a networking person, so I don't genuinely know what the state of the art is in this respect. But certainly, you can set up firewalling rules that would allow you to limit what access any specific container has to other containers and to the rest of the world. So it's certainly technically feasible. It would surprise me if nobody has done work in this field, but it's just not one that I have paid a great deal of attention to.
All right. Thank you so much, Matthew. Round of applause, please. Matthew will be around, I think, for a little longer. Hopefully we can grab him for a beer afterwards, so there'll be more time to ask him questions. Thanks so much, Matthew. Matthew's talk was a perfect setup for Mark, who's going to go deeper into security, specifically in relation to Sysdig Falco. So please welcome to the stage Mark Stem.
Hello. Well, I was first going to talk about how awesome SE Linux was for an hour, but maybe I shouldn't do that. So I guess I'll just do the second half of my talk where I talk about Falco. Uh-oh, we're going to have to take another 20-minute break? Let's see. Do I have to do something to switch my... Is it saying it? I can just do HDMI then. Okay. So sad. Who said Macs are easy to use? Should I plug it and plug it in again? Or? Okay. I don't know. Why did the container cross the road? I don't know. Yeah, I don't have a punchline. I just thought maybe somebody else could fill it in. My singing's limited to lullabies for my kids, so you guys don't want to hear that. You do the what? Oh, I'm getting music off the stage.
All right, folks, hold on for 1 second. It looks like the AV system can't handle all this amazing content. Restart the whole box?
Yeah, I'm restarted. Just get everything going. Oh, there we go. All right, let me unplug this. Oh, I don't know if I should do that. All right, so let me do some setup myself because I gotta restart some VMs and stuff. Did you guys hear about the no escape key for the new MacBooks? That's horrible. How am I ever going to live?
While Mark's finishing his setup, after the Falco session, we will do a Q&A and wrap up with the Sysdig engineering team. So prepare your best questions. It's your last opportunity to stump the Sysdig team. And Gianluca really wants to be stumped today. That's the goal.
Okay, we may have to do some parts a little less cut and pasty than I liked, but we'll make it happen. All right, here we go. It'll only take 10 minutes, whatever. Okay, so I'm Mark Stem. I'm going to talk about Falco, our new open source security software. Just to start off with a bit of an analogy, let's kind of think about home security and the different approaches that you have to keeping bad guys out of your house. So you have a bunch of stuff which is kind of designed to protect the exterior and prevent people from getting in, right? You have locks on the doors, you have bars on the doors, you have sensors so they can't open the window or break into the window. You might have cameras. All this stuff is designed to make sure that somebody cannot get in, right? But there's other stuff as well. There's maybe you have cameras inside your house. Maybe you have motion sensors inside your house. The goal there is a little bit different. The goal there is not prevent someone from getting in. It's to detect that someone is inside and is, I don't know, going for your safe or something, something like that. So it's two different styles of protection. And they're both really important, but they do different things. So if we think about taking that analogy and bringing it over to computer security, we kind of have the same kinds of breakdowns. We have stuff that prevents people from getting in. You have passwords. You have two-factor authentication. You fix the software vulnerability so someone can't exploit it and get in. You have firewalls so they can't get in on some crazy port. But you also have other stuff. It'd be nice to detect that somebody has gotten past that first line of defenses and they're running rampant within your system. This is very common in the network space. There's a whole suite of products called intrusion detection systems. And what we thought is, let's try to build something in that space. So that's exactly what Sysdig Falco is for. It's taking the second approach, which is, let's detect that unauthorized behavior is going on and let you know about it so you can do something about it. And just like the traditional system, both methods are really important to get full protection. So just a little bit more detail about what Sysdig Falco is. It's, the one-sentence summary is that it's a behavioral security monitor. So what that means is you define rules that identify what the suspicious behavior is, and we'll see in some of the examples, but the way we define them is by using the same kind of relatively easy to use things that you see in Sysdig. So the heart of each of these rules is basically a Sysdig filtering expression. And so because of that, you get all the support that Sysdig already has. It works with containers, it works with orchestration environments, it works with nice filters on system calls and arguments and all this stuff. So you get a lot of immediate power very quickly because it's using everything that Sysdig has. And then we also have notification methods. So when the rules detect some suspicious behavior, you can send notifications. You can write to syslog, you can write to a file, you can send an email, you can post to a Slack webhook, which we'll be using in our second talk, the contest, so that's really important. And it's open source, so it's just like Sysdig. It's on GitHub. Use it, download it, give us updates, give us new rules, so please be a part of the community and help us out. So just some examples of the kind of stuff you can do. So let's see, your left-hand side is things you might want to detect, and the right side is how you would detect that stuff using Falco. And if you look at the right-hand side, that really does look like Sysdig command lines, right? And it's not a coincidence. It's because they're using the same stuff. So maybe you want to see that somebody's running a shell in a container. If you think about containers as a way to implement microservices, you don't really, maybe for debugging and ops stuff, but when you're running, you don't have general shells where you're just poking around and doing stuff. So maybe you want to detect that because that might be a great way for an attacker to start running rampant once they've exploited some vulnerability. And so on the right-hand side, that's what the Falco rule will look like, is the container not on the host, and is the process name being bash, is somebody's trying to run bash, or any other shell. Is somebody trying to overwrite system binaries? So are they going to overwrite ls with my rootkit instead of ls or something? And so that's a good thing to detect, and the way to detect it is it a write? And we'll get into this a little bit. This is actually a little macro that allows you to share some common stuff around. And is the target of the write, does the directory of that, is it one of these common binary directories? Is somebody trying to switch namespaces on you? So you should be mostly fine within Docker because there's a setcomp profile that prevents you from calling that particular system call. But maybe from the host, you don't really want general processes masquerading as containers or something. So that might be something that's of interest that you want to keep an eye on. And so that's how you detect that. So just like the bin thing, you can write files below /dev. And then my favorite is, I saw a lot of people have the tape over the camera. I should do that. I don't do that for this laptop. But another way to make sure that nobody's got access to your camera and you don't know it is to do it like this. So is somebody trying to open a file, and the file is your video device, dev video, and is the name of the process not one of the processes that you would expect to be doing that? So if it's not Skype or WebEx or whatever your favorite is, that's a suspicious activity, and that's something you want to keep an eye on. Okay, so I'm definitely an engineer because I can't write architecture diagrams that don't just look like boxes, but Jean-Lucas was much better, but maybe I should go steal his. But this kind of shows how the Falco architecture works. A lot of it is using the same stuff that we saw in Sysdig, and I'll just kind of show how Falco graphs into it. So we start with this Sysdig probe kernel module. It's tapping into the stream of system calls that happening on the machine, and everything's flowing up to user space. We have the Sysdig libraries that kind of turn the raw system calls into higher order events. So we're building up state. We're decorating the events to say, okay, this thing actually happened in this pod or in this container, in this orchestration level namespace or deployment or something. And the part where the Falco uniqueness comes in is in two ways. So the first place it comes in is that Falco runs with a set of rules, and the rules basically define a set of filtering expressions that run against all the events. And so that's kind of the first box with the arrow. The rules turn into the filtering expressions, and so events come in, and then only suspicious events come out. So the rules are trying to detect bad behavior, so if something doesn't match any rule, it's okay. But let's say something does match one of the rules, so it's some suspicious thing that you want to know about. The second way that the Falco rules kick in is they help define the alerting message. So we've talked about earlier today that you can use Sysdig as a filter to filter events, but there's also, we talked about -p and -bk, and basically you can use those same terms to define a message which is populated with a mix of plain text and things from the actual event. So that's where the second part of the rules kick in. They help define the message that you want to send. And then Falco has its own configuration to basically say where that goes. So it goes to syslog file, all that stuff. So, how are we doing? Everybody making sense? Yeah? All right. So let's take a closer look at what the rules look like. Basically just a YAML file, pretty simple, nice and easy to read. It's a little different than Sysdig because we're baking a behavior into the rules, so you can't just put it all on the command line. So you got to put it in a separate file that you can read. So the YAML file contains three types of things: macros, lists, and rules. Macros are just kind of little snippets of filtering expression that you can use over and over just to give you some code savings. So for an example, you can have a macro binder, and it says, is the FD directory in one of these things? So then later in the file, you just say binder instead of repeating FD directory over and over and over. Lists are basically kind of a lot like macros. They just don't have to be filtering expressions. They're literally YAML lists, so they just get stuffed in whenever they're referred to. And rules, this is the interesting part. It basically has a name, a description, a condition, an output, and a priority. So this is like the meat of it. So, and a file will generally have lots of these rules and some macros and lists as well. Okay, so I mostly described all of this, but let me just go through the rules so we could go line, item by item. So every rule has a name that's used for the output string and also used for, we have some internal stats that are for like accounting purposes. You can see how many times a given rule hit and so forth. So the name is used to uniquely identify a rule. All rules have a description, so it's plain text. That gets used. There's like a help option, which is describe what all the rules are, and that gets put in there. So the condition, this is just the Sysdig filtering expression. In most cases, as long as you expanded the macros and lists, you could take that, cut and paste it into a Sysdig command line and run it, and then you would match the exact same stuff. Output, so this would basically be the -p argument to Sysdig if you ran it. And it's basically your mix of string, plain text and stuff from the matching event that goes into the notification. And then all alerts have a priority because, every system's got to have 25 different priorities that you'll never use except for warning and info. So yeah, if you can tell me what notice is for and give me a good reason, maybe I'll give you one of those coffee cards. Yeah. Okay, so we talked about the filtering expressions. Like we said, it's just like Sysdig, has all the support for containers and Mesos and Kubernetes that Sysdig has, so it's pretty great. If you look at the way the rules work, it's internally they kind of get turned into a big old OR. So it's literally take the first thing or the second thing, or so it gets really long. But we have some mechanisms to make that a little bit more efficient. One of them is to look at the event type of these events as they're coming in as an initial quick filter to kind of discard some branches of that big OR statement. So for that reason, all rules have to name an event type. So you have to be at least thinking about a little bit about what action is being done here. So, and that allows it to go a lot faster. When we first had the initial version where we're just going this or this or this or this, it was like really, really slow. Adding the event type filtering made it, I think like 10 or 20 times faster based on the workload. And we had a blog post about it too. Okay, so event comes in, it matches one of the filtering expressions, and now we have something that's going to be an alert, right? So the output field of that rule is used to format the event into a string. And so, like we said, it's a mixed thing of text and stuff that gets matched against the event. And then everything we talked about so far is the Falco rules file. There's a separate file, the Falco config file, that controls what happens with alerts, and then a couple other things that are like logging levels internally for Falco. But the important thing is that they're separate. So there's the rules, which is kind of your policy, and configuration is kind of preferences for how to act on the policy. And like we said, you can send all these different things. The shell one's really nice because you can do lots of stuff with it. So you can send emails, you can post webhooks. So that it's a nice, really general purpose one. So just like Sysdig, you can get it all the normal ways. You can get it via apt-get, yum. If you want to do curl and run it through sudo bash, I know some people don't like that. We don't like it either. We actually had a blog post on why that's not such a great idea, but like Matthew said, ease of use often trumps good security policies, so I guess we're a little bit of a victim of that as well. But go look at our blog post, and then we'll talk about ways to make it better. And you can run it as Docker just as easily, and then we have stuff on GitHub for how to install it. So, though I guess at this point you should have all already downloaded it and run it multiple times. So, this is old news to you guys. You can run it as a service when by default, if you install it via one of the package methods, it's like just a service you can run with a service or check config or so forth. You can also run it totally by hand. If you have your own rules you want to run it against, that will come in very handy for the contest. And if you have your own config file you wanted to run it again, trust me, this will also come in very handy for the contest. You can just say sudo falco, give it a rules file, give it a config file. And of course, there's -h in case you forget that. Here's the long Docker run command. So you have to type this, everybody write this down. No, just kidding. It's all on our GitHub, so you can copy it in. But basically, we have to, like Sysdig, we have to have some additional visibility onto the host machine. So we have to run privilege so we can access that kernel module's device. And we have to look at the Docker socket to get some Docker events and look at proc so we can see what's going on in the files, the processes. So it's a long thing, but there's justification for all those arguments. All right, let's do a demo. So this might take a second because I got to restart some stuff, but. All right, not too bad. Okay, here's that big long Docker run command. Look, I didn't even type it in. I just cut and paste it myself. Okay, so we've got it running. So by default, when you run it in the container, so this is running from a container. It just stays in the foreground and just is like, okay, I'm ready to go. It's matching against all the events, and when something triggers, it's going to write some stuff to standard out. So the first thing we'll do is we'll just do something really simple. Let's just right below bin. So let's just go touch a file. I'm a hacker, so I'll do bin hack. So what do you know? We have a rule that says, hey, did somebody try to write to a file? Oh, I'm sorry, should I make this bigger? Let's make this a little bigger. How's that for the people in the back? All right. Yeah, so we have rules that basically say, did somebody try to do an open of a file below bin for writing? And if it does, we have an alert, and here's the alert. Here, let me give you guys an overview of just all the stuff we're going to show. Look, we've already gotten through 2 bullets. So we are going to install it using Docker, look at the rules, and then just some of the stuff we're going to do. So we already showed writing through bin. We're going to try running bash inside a container to kind of break out of this microservice agreement that people have. We have this really fun program that does all kinds of evil things, and we'll show it doing all the evil things. We'll show what a really bad coder would do if they designed a REST API, and then how it can be exploited and how Falco will detect it. We'll kind of show some practices related to containers that, if you don't run your containers in kind of following best practices, how we can detect that. And we'll kind of show how, we'll show how Sysdig Cloud can be used related to Falco. So this is all open source, but we also have capabilities in our commercial product for receiving Falco notifications, and we'll kind of show how that's going on. Okay, so we were up to the shell in a container thing. Oh, let's see. Do I have it in here? Yep, there we go. Okay, so let's just run Python in a little container. So we're inside of the Python REPL. I guess this is a little bit of a weak example. The analogous thing is, let's say you've got like a Apache web server with Python, and you're trying to stay, pretty tailored to a service. You're not letting them do general things, but let's say somebody's smart, they know how to do at least a little bit of Python like me. And they're like, oh, well, I'm just going to get Etsy password by running it through a shell. Oh, yeah, it would also help if I get Etsy password. But I'll do it anyway. But you've already seen the punchline. Yeah, so we also have rules that say if somebody tries to run a shell in a container, then that results in a notification. So we did that, and hey, what do you know, there's the notification. What should we do next? Oh yeah, this one's fun. Okay, so when I was testing, I'm like, oh, I really need something that stresses all the different rules I have. So I basically went out and wrote the evilest program I could think of. So I said, okay, what are all the bad things that our rules do? And let me write a program that does all of that. So don't go run this program directly, because it's going to do things like remove things below bin and dev and SUID and all kinds of crazy things. But it's fun. It's great to run it in a container because you just wreck the container and then you just turn it off and it's OK. So we'll do that first. So just let me show you what the help does. Look at all this evil things we can do. So this is available on Docker Hub. So if you want to play with it and do evil things to your own containers, feel free. So we can do things like, most of these correspond to the things in the rules. So we can write below bin, we can write below Etsy, we can read things like Etsy shadow, files that you really don't want people to be reading. So for this is a fun one for SQL injection attacks. So like, what if you're running a SQL Server or MySQL, and then somebody sneak in a bad query and then break out to a shell or something? So we have rules that detect that, and so you get the idea. So let's just fire this up. Okay, so basically we're just going to run it where it loops over all the bad things and does one bad thing every 5 seconds. So it's kind of looping over everything now and say, hey, what do you know? Falco's starting to detect everything. So hey, look, we got all the bad things that you want to do. So I'm sure it'll be great for demos where I don't have to do the demo because I don't have to think of all the bad things myself. I can just have this program do it. Let's do Sysdig Cloud now. Okay, so how much bigger can I make this? So you can see so the way it works in Sysdig Cloud is our agent has Falco capabilities in it, and when it detects suspicious behavior, it uploads that to Sysdig Cloud, and you can see all of that stuff as events. It's a feature we're rolling out now-ish. We're talking to customers, kind of staging it out. But you can see, this is a great audit log, and so you can see it's also being updated as I knew more bad things. So it's saying what the action is, and when it was, and where it was, and all that stuff. So it's really good visibility. I think the next thing we're going to want to do is really kind of close the loop. So wouldn't it be awesome if you were in something like Kubernetes and you could just suspend the pod where one of these things was happening and then go try to use Sysdig to do some diagnosis and figure out what's going on. So I think that's, if we can close that loop, that's going to be pretty amazing stuff. OK, so the last thing we'll do is, here, let me kill this guy. Actually, let me kill this guy too. So I forgot to show the node.js thing. So, OK, so for those of you who might be familiar with node.js, this is just a sample, simple node.js application based on Express. And let's say I'm not a really good developer, but I have these endpoints. I'm like, oh, I really need some kind of general purpose thing that allows me to run things on the other side and just send the results to me. And I'm too lazy to actually think about security or sanitization or anything. So I'll just make up an exec endpoint that basically says, hey, if somebody does a get of API exec blah, I'll just go run blah. And this is great. It's super general purpose. I can just, I don't have to actually write any code. So that's awesome. I'd get fired if I actually did this, but just for fun, we'll do that. So I've got a little Docker Compose environment where I've got all these pieces put together. So I've got, oops, got to be in the right place. So we've got and I got to remove the old Falco. OK, so we got a copy of Falco running. We got a copy of this Express server running. So everything's all up and loaded. So let's try getting some APIs. So, oh, great. So let's do API exec ls. OK, it does ls on the target machine. Let's do pwd. Oh, that's great. We found a directory. Look, the hackers figured it out. We'll just run bash and we'll get a shell and we'll be able to do anything. We'll do rm-rf, slash. But that's OK. Falco detected that. So this is another example of that don't run general purpose shells in containers. And it said, hey, look, you were node.js and you really shouldn't be spawning shells. And somebody tried to. So it results in notification. You should go figure out what's going on. OK. And the final one we'll do run Falco again, get it up and running. So Falco is, as container aware as Sysdig is, and Sysdig has capabilities to do things like use the Docker API to figure out what mounts a given container is using, or figure out how the container was launched. Was it run privileged or not? So we actually have rules in the rule set. Oh, let's run this one. Let's see. Yeah, there we go. So we actually have rules in the rule set that say, hey, is somebody doing actions in a container that's running privileged? And is it not one of the containers that we know about that's expected to be running privileged? So if you do that, hey, look, Falco detects that, sends notifications. Another kind of bad practice for a container is although we do it, or maybe not bad practice, a practice that you want to keep an eye on it. Yeah. Another thing with Docker, you can mount any files, any path from the host into the container. So you could mount Etsy Shadow, you could mount proc, you could mount bad things if you're not really careful. So we also have rules in the default rule set that say, hey, is a container running where it's done a mount and the thing it's mounting from the host is a sensitive path? And so there's macros for that. So proc is named as a sensitive path. So if you do that, hey, look, we have rules that say, it's doing actions, and the container where it's running has one of these sensitive mounts. So it's another way to help enforce some policies for best practices for running your containers. So I think that's about it. Let's see. I think that was everything. Yeah, we got everything. OK, so all the normal links. We got a website just for Falco. We got a mailing list. We got a public Slack channel. Hopefully many of you have joined it today. We got a blog. It's got a bunch of blog posts talking about use cases, more details about the rules and so forth. So, oh yeah, please give us code. Please take our code. All that stuff. Look at our wiki. And almost everything I ran was via Docker. So we have Docker Hub for everything. So that's it. Any questions on Falco? I think there was one over here.
Yeah, hi. So I read the GitHub page, and it says that it is intended to be run as a service. So is it possible to have like a master-child kind of architecture where one server, which is a monitoring server, gets all the alerts from my child server where it is running? And the second part of the question is that is it possible to suppress alerts? Like there might be scenarios where it might be a false positive for a certain, like a certain use case. So is it possible to suppress those alerts as well?
Yeah, so for the first thing, although we send notifications, we're not going to be a replacement for your Nagios or whatever. So I think if you want to build a distributed alerting system out of the open source Falco, you should kind of use us as the clients, as the thing feeding into something you already have. So like you said, we can spawn to a shell, so we can send it wherever, and then after that, use what you already have. For the second thing, sorry, what was the second thing? Oh yeah, suppressing, right. Again, that's mostly best done by your existing thing. We do have the ability to, there we go. We do have the ability to turn rules on and off. There's a enabled flag that you can do. And I think we don't have this, but it's always been a nice way to think of like context sensitive modes. Like, so you could maybe put it in admin mode, and then a lot of the rules will get turned off. Like if you're actually doing an install of new software, then it's okay to write below bin, and only during that period. But then after that, you can't. So, but we don't have that now. It's we'll take all pull requests. So, yeah, I think there's another question.
Yeah, for the first question, I think at one point you showed that sometime in the near future we'll be able to actually see the notifications on Sysdig Cloud.
Yeah.
Is that not an aggregation of?
Oh yeah, that is. Like I said, I tried to qualify it with open source. We definitely have a commercial product. We want everyone to use it. It's very distributed. Please come talk to us about that. So.
Yeah, Nagios also has an enterprise and an open source. So.
Yeah. No, you're right. We don't quite have that level of sophistication for the open source thing. It's very one node at a time. So.
Sure.
More questions?
Last chance. Last chance till Mark does his next presentation.
You guys should be asking questions, because in about 5 minutes you're going to wonder, hey, how does this thing work? Because you're going to be writing some rules based on it. So that's right. I have plenty of hints. It'll be fine.
All right. Should we do this?
Yeah, let's do it. OK, so we got a contest, and there's prizes. And here, I'm supposed to show off the prize. You guys all want it. OK, so it's a prize. So come get the prize. Here, let me just get my slides up. OK, we're going to see how this works. We're going to have everybody log onto a machine and try to find some suspicious activity. There's a lot of you. We got the biggest box we could get from Amazon. We think it's going to work, but let's find out. Okay? And so just remember, you're all going to be logging on to the same box as the same user. So don't rm-rf star. Make a directory just for you. Go in that directory. Do everything there. Be a nice person. Don't peek or delete everybody else's directory. So just think about that, okay? Okay, so here's the contest, right? So we're going to use Sysdig and Falco to basically find some suspicious activity. With Sysdig, you're probably going to be finding the activity. With Falco, you're going to be writing a rule that encompasses the suspicious activity you found, and you're going to send it to us. We have a public Slack channel, sysdig.slack.com. There's the channel. And basically, we want you to basically send a notification to there. And whoever does it first with the important information gets a prize, gets this prize, okay? Oh, look, see, look, it's the same thing. So let's, if I was doing the prices right, I'd do like this, right? It's an HD camera, RTF, anyway, so it's pretty awesome. Okay, so here's the details. There's the pieces of paper, I think, that are just now on the post, so if you want to log in. So we got this machine. Here's its IP address. There's a username and password. It should have Sysdig and Falco on it. And I put some sneaky software on there. And I'm not going to say much else about what it does. So it's doing something that's pretty suspicious, something you would definitely not expect normal software to be doing. And there's an IP, so the way we can get you to prove that you did it is that there's an IP address involved, okay? So it's doing something related to an IP address. We want you to find that IP address and basically send it to us. And it's not, not the one that you logged in, right? And not the 172.1. There's a one that's not in these ranges, okay? Okay, so identify it. You can use Sysdig or Falco or whatever it else. And so we want you to write a Falco rule. The best way to do that is probably, I'm sure you totally memorized my format, but the best way is probably go take the existing rules file and see what it looks like and modify it for your purposes. Just take the format and just make one rule out of it. So that's in etc falco_rules.yaml. If you log into the machine, we have a lot of stuff in the etc message of the day that it'll just pop up. So you don't have to worry about cutting and pasting this horrible Slack webhook. That's already in the message of the day for you, okay? And also we've got a hint about the way to do the transformation from R output as JSON. Hey, maybe you'll find the JSON output useful, hint, hint. The way to transform that into the way that the Slack webhook handles it is this command. This is also in the message of the day, so you should just be able to cut and paste that. The quotes on the end of the string are very important. And remember to run Falco with a rules file, it's -r. The way to run Falco with a -c file is -c. So basically, take the rules as an example of the rules you want to write. Take the config from etc falco.yaml, copy that, remember, to your own directory, your own user directory, to start with that as the basis, modify it to give you the output format you want, and run Falco, and let's see who can get to the public Slack first. What? Oh yeah, there's these pieces of paper that we put on, yeah, okay. Let's see. Yeah, I'll go back. I think, oh yeah, so I'm on the hints section. So the way I'm going to do it is we'll see how things go. I have progressively easier hints to give out. So I think by the end somebody will be able to get it. But here's the IP address and the account again. That R is a 0, not a big O. So the letter after the R is a 0, not a big O. Maybe what else we could do is if people have questions about, like, I can't log in or something, like raise your hand and we could do the buddies come over and help you out. We do want to let the investigation and the rule writing be up to you, so we'll start with that. I'll kind of start it for 5 minutes. Oh, and here, I don't know if I have my, here, let's do this. And I have my public Slack. Has anybody gotten it yet? Well, somebody put the password in the public Slack channel. That's a good idea. Okay. And the faster we win, the faster we don't have to listen to this music. So. That's right, yeah. Wait, the longer we go, we'll make it louder and louder. Here, I should actually run top or something, make sure it's not falling over. Actually, here, let's do it over here. All right, that's not horrible yet. Nice, I see people using Sysdig. Good job. And some Falcos. Also, like, say bingo if you think you got it, so I go back to the Slack thing.
Raise your hand if you have any questions as well. Someone will come by and help you.
And don't forget to make a directory below the directory. Okay, people ready for hint number 1 yet? This one I think is a good one. Okay, so hint number 1, it's related to something below Etsy. So a good way to see all the things that are doing things related to Etsy is this Sysdig command. So I think if you do this, that might help point you in the right direction. What? What? Yeah? Yeah, you just do that same password.
Yeah, that doesn't seem to be working. Sysdig is not allowed.
Oh yeah, I could make it allowed. Well, I was. Oh, you trying to do Sysdig or Sysdig?
Sysdig.
Oh yeah. But you got Sysdig to work, right?
No. Yeah, Sysdig works. Oh, sudo Sysdig.
Yeah, sudo Sysdig should work. You may have to type your. Yeah, there you go. You got Sysdig. Let me see if I can quickly make Sysdig usable. All right, gonna do VI. Sorry, you think you got it? Okay, hang on. Let me just add Sysdig just in case people wanted it. Yeah. Yeah. Don't just type in the thing you think with the. So I think Sysdig should work now. Do you want to give it a try? It works? Okay. And somebody thinks they posted? Let's see. Yeah, okay. So you're very close. I shouldn't show it for too long. Whoever that was, that's the right information, but I would also like you to write a Falco rule that detects that activity and sends it to the Slack webhook. So that, remember the Etsy message of the day? You just cat that, or I guess you have to log in, log back out. It has the thing to add to your config, your Falco config, to make the whatever happen. So you'll want to take a custom config, take a custom rule, put that all together, and then see how we're doing. And we'll move on to the next hint, I don't know, 4 minutes or something like that. Because I think the next thing we do is have some beers, right? So.
Yeah, I was just going to say that. So
God help me if I'm the one in between us and the
who
beers.
wins the drone, everybody gets drinks and food.
Yeah.
After this, we'll do a quick wrap up with Loris and team, and then we'll have some drinks and food.
And when you write your rule, make sure you include something in the output that says who you are, because when it comes through the webhook, it's just generic, so we won't be able to tell who's who. Oh yeah, and if anybody's live streaming, go for it. If you guys win, we'll make sure you get a drone somehow. And we'll have a drone here. We'll give drones and drones and
We'll
drones.
just fly it to them.
Yeah, that's right. Yeah. The battery should, I mean, it's totally transcontinental, right? Yeah, next hint. Okay, so we've already talked about it's something related to Etsy. So you may have found the program that might be doing the bad thing. So it might be a program called CPP. It's not. Guess what? It's not the C preprocessor. It's some other evil program. So if you specifically want to look at what that program's doing, you can say proc name equals CPP. If you even more specifically want to say, hey, well, we said it's an IP address, so it's related to network stuff. What are the networking related events? So here's a Sysdig command to give you that. Might be able to narrow it down a little bit. A Falco, yeah, it has to detect it, right? So you basically have to have a condition that matches the event related to the IP, and an output that names the IP. And your friend is Sysdig dash, I think. I can still run, but just a second. So Sysdig dash L is your friend. It will show you all the different things that you can put in filtering expressions as well as outputs. So those are good things to look for when you're trying to pull out the IP address in question. So I'm okay. Are you able to log in still? Yeah, okay. Maybe it's that bad. I should run Loris's spectrograph so we can watch the network crumble as we're doing this live. Oh yeah, sorry, I was just checking to see. So it looks like somebody else also got the right information, though it's not coming as a Falco notification. So we're definitely, you guys are close, whoever you are. Anybody feel like they're stumped on any phase? Like, I did the instructions wrong or something? Because I definitely don't want that to be a barrier, but. Okay, we'll give it a couple more minutes and then we'll do the next hint. Drones don't come cheap. You got to earn it. Make sure we're not crumbling. Oh, no problem. Okay, we'll move on to the next hint. I think this is, now we're really just talking about navigating the files and so forth. So we know it's CPP. If you run the Sysdig command, I'm pretty sure you can see what the IP address is. So how do you need to format that into a string that might go in your notification? So running it this way would be a good option. So this says, let's get a format which just has the IP address in question. So it's going to say, is the event a send to? And if it is, put the command line and the IP in the port. In your rule file, it would be very good to include your name. That would be good. Oh yeah, because you're, well, no, I think you get your own, right? Oh yeah, I did, you know what, I did that because I didn't want you to inherit, yeah, sorry about that. I didn't want you to inherit somebody else's history when you logged in. When we do this next year, I'll get a real true root thing going. Here, everybody's logged in by now. Maybe I can just take that thing out. Would that help? Oh, okay. Okay. Yeah, run in Emacs like I do, and then you don't have to do anything else. There's some I forget. It's like some. Oh, okay. Oh yeah, because it won't be login, so I think I put it in profile. And, yeah. Okay, so how are we doing? Anybody get closer? Yeah, people's got the information, so now it's about formatting and packaging. Okay, do a couple more minutes, and then I think the next hint is about what the rule might look like. You think you got it? Oh, look at this. Well, this is something. Oh wait, now there's a whole bunch of stuff coming. Yeah, here we go. Okay, so we need some names though. So I see all the right information here and I see the webhook, but like I said, it's all generic. So just in that output string, put who you are. And then I think we'll have it. Let's see. I'll have to scroll carefully so I can see if I can find... Okay, well, while we're waiting, just one more hint for everybody. So here's what a role might look like that encompasses all the information we've learned so far. So the condition is matching, and then there's some scrolling I didn't quite have, but we got the condition that matches the thing happening. We got the output that looks at the IP address and so forth. So let me just go back and see if we've gotten some names yet. We got a name? I'm trying to just find it. I want to make sure I get first. The first person. I don't see any names of people though. Oh yeah, that's a... this should be an example? Yeah, I think in the config file I have the piping, at least the Slack webhook posting, but the whole thing, that would be a good idea. Okay, so I think if you were that person, so I think all you need to do is change your output string to just put your name in it. Oh, okay. So Kalu and Balu, you guys have the right information, but you're not posting to the Slack webhook yet. So this rule is a good start for that, and we'll do one more hint in a little bit, and then it'll be just a cut and paste test, because that'll be how to modify the Falco configuration to post the notification to the webhook. So remember, we have the rules, that's kind of the rules and policy, and then we have the Falco config, which is what to do when things match the rules. Okay, so a lot more stuff, but I don't think it's... Do we have a bingo? I'm still scrolling. Oh, okay, yep. All right, we have a winner, Kalu. Good job. Though I don't think you're a system binary, but we'll let it go.
Well done.
We'll let it
well
slide.
done.
Okay, but just for fun, the last little piece for anybody who was trying to get all the pieces together, you had to change JSON output to true, and here was your cut and paste. So I think most of this was in the message of the day. You also needed to enable the program output. I think if you had all those pieces. So everybody here, just start posting like mad to the Slack channel. But all right, who's Kalu? Who's the?
All right, come on up. Let's get you this.
Free drone for you, free beer for us.
Well
Oh.
Round of applause. Well done. Sorry to cut you off.
Well done. Good job. The well, you mean? Oh, sorry. This one I think is the rule that should work. Okay, well, here, let's drink beer and do the wrap up, and then we can chat and get all the pieces together. All right, well, thanks. I hope you had fun.
Thanks, Mark. All right, long day, lot of information. I just wanted Loris to do a quick, maybe, I don't know, hour-long wrap-up session, couple hours?
Couple of hours. So just checking with you guys if you feel like the guy on the left or the one on the right after the full day. So seriously, just wanted to thank everybody to be with us today. We had really a great time being with you. I hope the program that we put together had enough quality and enough diversity to bring value to you guys. We're around. There are drinks now. We'll be there. So please feel free to come and give us your feedback. We'll try to do our best to incorporate it and learn to make this even better next time we do it. For the moment, thank you very much and enjoy your beers. Apurva, this question is for you. The question is about slides, where they will be and how you get them.
Yes, absolutely. So we actually already have most of the slides up on SlideShare. So if you just search for SlideShare and Sysdig, you'll find them. Once we have all the video and we're going to do a little post-processing on it, we'll also have that up most likely on the Sysdig website itself. Since we have all your email addresses, we're going to send you that information, as well as we'll send you a post-event survey. So anyone who could fill that out, there will probably be a prize involved in filling that survey out too, but we'd really appreciate your feedback. This is the first time we've ever done this, and feedback would be really appreciated. Thanks, everybody. Please meet us outside for a drink.
Thank you.
Thanks, sir. Thank you. Giving this back to you. Thank you so much.